Close your eyes if you'd like, or simply let your gaze soften as we drift together through some of the most calming truths about our universe. This is a space where scientific facts become soothing companions for rest, reflection, or sleep. No urgency here. No dramatic reveals. Just the quiet, steady rhythm of cosmic reality, explained softly, simply, and completely at your own pace. Over the next few hours, we'll explore how starlight reaches us, how planets form in silence, how galaxies move like slow rivers through space, and how time itself flows differently across the cosmos. Everything here is real, everything is gentle, and everything is designed to help you relax. You don't need to remember anything. You don't need to stay awake. Just let these facts wash over you like waves on a distant shore. Let's begin our peaceful journey. The gentle light of distant stars. Take a comfortable breath. And let's start with something simple and beautiful. The light you see from stars at night. That light has been traveling for a very long time. Some of it has been traveling longer than human civilization has existed. And it travels in perfect silence, crossing the emptiness of space without sound, without hurry, without effort. Light moves at a specific speed, about 186,000 miles per second, or roughly 300,000 kilometers per second. This sounds fast, and it is. But space is so vast that even at this speed, light takes years to cross the distances between stars. When scientists talk about light years, they simply mean the distance light travels in one Earth year. 1 light year equals about 5.8 trillion miles, or 9.5 trillion kilometers. The nearest star to our Sun is called Proxima Centauri. It sits about 4.2 light years away from us. This means when you look at Proxima Centauri in the night sky, you're seeing light that left that star over 4 years ago. You're looking into the past, gently, quietly, without any drama. The star you see is the star as it was 4 years ago. By the time its light reaches your eyes, 4 years have passed in complete silence across the black ocean of space. Many stars you can see without a telescope are much farther away. Some are dozens of light years distant. Others are hundreds. A few are even thousands of light years away. Each point of light in the night sky is a messenger from the past, arriving constantly, steadily, like gentle rain. Consider the star Betelgeuse, a red supergiant in the constellation Orion. It lies roughly 650 light years from Earth. When you look at Betelgeuse, you see it as it appeared around the year 1374, during the European Middle Ages. The light touching your eye tonight left that star before the Renaissance began. It traveled through space all this time, never stopping, never changing speed, moving through the darkness at exactly the same pace. Always. There's something deeply calming about this. Light doesn't rush. It doesn't slow down. It simply continues, steady and sure, covering unimaginable distances, 1 mile at a time, 1 kilometer at a time, for hundreds of years, for thousands of years. Some light from the most distant stars visible to the naked eye has been traveling for tens of thousands of years. Space itself is mostly empty. Between the stars, there is simply space, darkness, silence, the occasional hydrogen atom floating alone. Light passes through this emptiness without interruption, without friction, without obstacle. Nothing stops it. Nothing slows it. It just continues, peacefully, eternally. When light finally does encounter something, like your eye or a telescope mirror, it has usually traveled farther than any human will ever travel. That single photon, that tiny particle of light, has crossed a gap so enormous that our minds can barely comprehend it. And yet it arrives gently, softly, touching us with information from distant places and distant times. The Sun, our own star, is much closer than any other star. It sits about 93 million miles away, or roughly 150 million kilometers. Light from the sun takes about 8 minutes and 20 seconds to reach Earth. This means when you look at the sun, always through proper protection, never directly. You see it as it was just over 8 minutes ago. If the sun suddenly vanished, we wouldn't know for 8 minutes. The light already traveling toward us would continue arriving steadily, peacefully, until that final light arrived, and then darkness. But the sun won't vanish. Stars are remarkably stable. Our sun has been shining steadily for about 4.6 billion years, and it will continue shining for about another 5 billion years. That's an almost incomprehensible length of time. Billions of years of steady, reliable light pouring out into space in all directions, without pause, without change in rhythm. The light from our sun travels outward in every direction. Some of it falls on Earth, some falls on Mars, some falls on distant Neptune, and most of it continues past all the planets, past the boundaries of our solar system, out into interstellar space, where it will travel for thousands of years before encountering anything at all. Light from the sun that passed Earth today will reach Proxima Centauri in a little over 4 years. It will keep going, carrying information about our sun, our time, our moment, into the distant future, into the vast darkness, forever. Every star does this. Every star pours light out in all directions. Most of that light travels through empty space, never touching anything, never being seen. It simply exists, moving outward, expanding in an ever-growing sphere, getting dimmer as it spreads, but never quite disappearing. In a way, every star that has ever existed still has its light traveling somewhere in the universe. The universe is filled with ancient light, new light, and everything in between, all traveling together through the cosmic ocean. The distances between stars means something profound and calming. It means isolation, natural isolation, peaceful separation. Each star system is an island in space, surrounded by vast emptiness. The nearest stars to our sun are light years away. The next nearest are farther still, and beyond them, more stars, each separated from its neighbors by enormous distances. This isolation means silence. Space has no air to carry sound, and even if it did, the distances are too great. If the sun could make sound, and if that sound could somehow travel through space, it would take years to reach the nearest stars. No star can hear any other star. Each burns in complete and total silence, alone in the dark, surrounded by nothing but emptiness and the steady, outward flow of its own light. There's no loneliness in this isolation, though. Stars don't need company. They exist perfectly well on their own, burning steadily, pouring out light, held together by their own gravity. A star is complete unto itself, a sphere of hot gas, fusing hydrogen into helium in its core, balanced perfectly between the inward pull of gravity and the outward push of nuclear energy. This balance can last billions of years without change, without adjustment, just perfect, steady equilibrium, burning quietly in the dark. Our galaxy, the Milky Way, contains somewhere between 200 and 400 billion stars. Each one is separated from its neighbors by these vast distances. Each one shines in relative isolation. Each one pours light out into the darkness, and most of that light simply travels outward into empty space, never touching anything, never being seen, just existing, moving, continuing. When you look at the night sky from a dark location, away from city lights, you can see a few thousand stars with your naked eye, maybe 3,000 or 4,000 on a clear night. Each one is relatively nearby in cosmic terms, usually within a few hundred or few thousand light years. These are our immediate stellar neighbors, the stars we can see without help. But beyond them, there are billions more stars in our galaxy alone. Most are too faint or too distant for human eyes to detect. They exist nonetheless, each one shining, each one pouring out light, each one sitting in its own space in the galactic structure. The Milky Way is shaped like a flat disk with a central bulge and spiral arms extending outward. Our Sun sits in one of these spiral arms, about 2/3 of the way from the galactic center to the outer edge. The galaxy rotates slowly, very slowly. Our Sun orbits the galactic center at a speed of about 515,000 miles per hour, or roughly 828,000 kilometers per hour. This sounds fast, but the galaxy is so enormous that it takes our Sun about 230 million years to complete one orbit around the galactic center. This length of time is sometimes called a cosmic year or a galactic year. Think about that for a moment. 230 million years for one orbit. The last time our Sun was in this exact position in the galaxy, dinosaurs had not yet evolved. The last time before that, life on Earth was still mostly confined to the oceans. And yet, despite this enormous orbital period, the motion is smooth, steady, continuous. The Sun doesn't speed up or slow down. It doesn't change course. It simply continues its long, slow path around the galactic center, taking all its planets with it, moving through space at a constant, peaceful pace. All the stars in the galaxy are doing the same thing. Each one orbits the galactic center at its own speed, depending on its distance from the center. Stars closer to the core orbit faster. Stars farther out orbit slower. The entire galaxy rotates like a vast, slow pinwheel in space, taking hundreds of millions of years to complete one rotation. There's no hurry, no urgency, just slow, majestic rotation driven by gravity, continuing as it has for billions of years. The light from all these stars travels in straight lines through space. Photons don't curve unless gravity bends them, and in most of space, there isn't enough gravity nearby to cause noticeable bending. Light simply travels in perfectly straight lines, at constant speed, forever. When you draw a line from a distant star to your eye, the light has followed that line, that exact path, across space. It hasn't wandered. It hasn't spiraled. It came straight to you. This directness is part of what makes starlight so reliable. When astronomers point telescopes at distant stars, they know the light is coming from exactly where the star appears to be, allowing for the star's motion across the sky. Light doesn't get lost. It doesn't take detours. It follows the straightest possible path from source to destination. Sometimes, light from distant stars passes near massive objects like galaxies or black holes, and gravity bends the light's path slightly. This is called gravitational lensing. But even then, the light doesn't curve randomly. It follows the curvature of space itself, created by the massive object's gravity. Space can be curved by gravity, and light follows that curvature, but always taking the most direct path through curved space. Even bent light is following the straightest possible route through the geometry it encounters. Most light, though, travels through regions of space where gravity is weak and space is essentially flat. These photons travel in perfectly straight lines, unaffected by anything, for light years or millions of light years. They cross the vast emptiness between galaxies, between galaxy clusters, through regions called voids where almost nothing exists, just empty space, dark and silent. The universe has many of these voids, regions hundreds of millions of light years across, containing very few galaxies, very few stars, very little matter. Light from distant galaxies crosses these voids without interruption, without change. The photons that began their journey on one side of a void continue unchanged to the other side, traveling for millions of years through nearly absolute emptiness. In these voids, a photon might travel for millions of years without encountering a single atom. Space is that empty in these regions. Just darkness and light passing through, and time passing silently. There's something profoundly peaceful about this. Vast regions of the universe where essentially nothing happens. No stars forming, no supernova exploding, no planets orbiting. Just empty space, stretching for hundreds of millions of light years in every direction, with the occasional photon passing through on its long journey from somewhere to somewhere else. Between these voids, matter collects into structures. Galaxies cluster together in groups and clusters, and these clusters arrange themselves along filaments like beads on cosmic strings. These filaments form a web-like structure throughout the universe, with voids in between. This is called the cosmic web, and it's the largest scale structure in the universe. Gravity pulled matter together into this pattern over billions of years, slowly, gently, without drama. Light from galaxies in these filaments travels out in all directions, including through the voids. Some of that light has been traveling for billions of years, crossing void after void, filament after filament, making its way through the expanding universe. The most distant light we can detect comes from galaxies so far away that their light has been traveling for over 13 billion years, almost since the beginning of the universe itself. The universe is about 13.8 billion years old. This means the oldest light we can see has been traveling for most of the universe's existence. This light left its source when the universe was young, when the first galaxies were forming, when stars were first beginning to shine in great numbers. That light has been traveling ever since, steadily, peacefully, crossing the expanding universe, until it finally reaches our telescopes now, today, in our time. When we detect this ancient light, we're seeing the universe as it was billions of years ago. We're looking back in time, across unimaginable distances, seeing galaxies that might not even exist anymore in the same form. Those galaxies have continued evolving, changing, perhaps merging with other galaxies. But we see them as they were, frozen in time by the speed of light and the vast distances involved. This is one of the most remarkable facts about astronomy. We can't see the universe as it is now, everywhere. We can only see the universe as it was, at different times in the past, depending on distance. Nearby stars show us the recent past, just years ago. Distant galaxies show us the ancient past, billions of years ago. Every direction we look, we're looking into history. And all of this is delivered to us by light, traveling steadily through space, never stopping, never slowing, carrying information across time and distance. Light is our messenger from the cosmos, our connection to everything beyond Earth. Without light, we would know nothing about the universe beyond our immediate surroundings. With light, we can see across billions of light years, into the distant past, to the edges of the observable universe. The observable universe is limited by the speed of light and the age of the universe. Since the universe is 13.8 billion years old, and light travels at a finite speed, there's a limit to how far we can see. Light from objects farther than about 46.5 billion light years away hasn't had time to reach us yet. That distance, 46.5 billion light years, is roughly the radius of the observable universe. Beyond that distance, there might be more universe, but we can't see it yet. The light from those regions hasn't reached us. This doesn't mean the universe ends there. It just means that's as far as we can currently observe. The universe might be infinite, extending forever in all directions. Or it might be finite but unbounded, curving back on itself in ways that are difficult to visualize. We don't know yet. What we do know is that the observable universe, the part we can see, is already unimaginably vast and filled with light traveling in all directions, from all times, all arriving here now to be detected by our instruments. Some of this light is visible light, the kind human eyes can see. But most of the light in the universe is invisible to human eyes. There's infrared light, which is slightly less energetic than visible light. There's ultraviolet light, slightly more energetic. There's radio waves with very low energy. There's microwaves. There's X-rays and gamma rays with very high energy. All of these are forms of light, different types of electromagnetic radiation, all traveling at the same speed through space. Stars emit light at many different wavelengths. Our sun emits most of its light in the visible range, which is why human eyes evolved to detect visible light. It's what's most abundant from our sun, but the sun also emits infrared light, ultraviolet light, and small amounts of other wavelengths. Other stars emit different distributions of light depending on their temperature. Hot stars emit more ultraviolet and blue light. Cool stars emit more infrared and red light. When astronomers study distant objects, they observe at many different wavelengths. Each wavelength reveals different information. Visible light shows us where stars are and how they're moving. Infrared light can penetrate dust clouds and reveal star formation happening inside. Radio waves can show us cold gas clouds between stars. X-rays can reveal extremely hot gas and energetic processes. By observing at many wavelengths, astronomers build a complete picture of what's happening in the cosmos. All these different types of light travel through space together, invisibly, silently, crossing the vast distances between stars and galaxies. At any moment, countless photons of all different energies are passing through the space around you, traveling from distant sources, on their way to destinations farther still. You can't see most of them, and they pass through you without effect, but they're there, constantly, filling space with invisible light. Even empty space itself isn't truly empty. Quantum mechanics tells us that empty space is filled with quantum fluctuations, brief appearances of particle-antiparticle pairs that pop into existence and then immediately annihilate each other. These fluctuations happen constantly, everywhere, even in the deepest voids between galaxies. Space seethes with this quantum activity at the smallest scales, though it's completely invisible and has no effect on anything at larger scales. There's also something called the cosmic microwave background radiation, or CMB. This is light left over from the early universe, from about 380,000 years after the Big Bang. At that time, the universe cooled enough for light to travel freely through space for the first time. Before then, the universe was too hot and dense, and light couldn't travel far before being absorbed and re-emitted. But once the universe cooled below a certain temperature, light could travel freely, and it's been traveling ever since. This ancient light fills all of space. It comes from every direction equally. It has been traveling for over 30 billion years, getting stretched by the expansion of the universe into longer and longer wavelengths. Originally, it was visible light and ultraviolet light. Now, after billions of years of expansion, it has been stretched into microwave wavelengths, invisible to human eyes but detectable by special instruments. The CMB is incredibly uniform. It is almost exactly the same temperature in every direction, about 2.7 degrees above absolute zero. There are tiny variations, less than 1 part in 100,000, but these tiny variations are important. They represent slight differences in density in the early universe, seeds that later grew into galaxies and galaxy clusters. But to a first approximation, the CMB is perfectly smooth, perfectly uniform, coming equally from all directions. This uniformity is deeply calming in its own way. The universe, at its largest scales and earliest times, was remarkably smooth and homogeneous. No large structures yet, no galaxies, no stars, just hot gas gradually cooling, filling all of space evenly. And light from that time has been traveling through space ever since. still filling all of space evenly, still arriving from all directions, still carrying information about those early moments. When you look at the CMB, you're seeing the universe as it was when it was only 380,000 years old. You're looking back across 13.8 billion years of time to an era when nothing familiar existed yet. No stars, no planets, no galaxies. Just hot gas beginning to cool and light beginning its long journey through time. And that light has been traveling ever since, peacefully, steadily, crossing the expanding universe, getting stretched by the expansion, but never stopping, never disappearing. It's still here, all around us, invisible but real, a constant reminder of the universe's beginning, still present, still detectable, still carrying information from that ancient time. The expansion of the universe itself is a gentle process. Space expands smoothly, steadily, everywhere at once. This expansion doesn't pull things apart violently. It simply increases the distance between distant objects gradually over time. Things that are close together, held together by gravity or other forces, don't expand. Galaxies don't expand. Stars don't expand. Planets don't expand. Only the space between distant galaxy clusters expands, increasing the distance between them at a rate that depends on how far apart they are. The expansion rate is described by Hubble's constant. Currently, space expands at about 70 kilometers per second per megaparsec. A megaparsec is about 3.26 million light-years. This means for every 26 million light-years of distance between two objects, the space between them expands at 70 kilometers per second. For objects twice as far apart, the expansion is twice as fast. For objects 10 times as far apart, the expansion is 10 times as fast. This means the most distant observable galaxies are moving away from us at speeds close to the speed of light, not because they're moving through space that fast, but because the space between us and them is expanding that rapidly. This expansion is smooth, continuous, and completely peaceful. It's not an explosion. It's not galaxies flying apart violently. It's simply space itself increasing in size, gradually, steadily, everywhere. This expansion has been happening since the Big Bang, 13.8 billion years ago. For most of the universe's history, the expansion has been slowing down gradually, pulled back by the mutual gravity of all the matter in the universe. But about 5 billion years ago, the expansion began speeding up again, driven by something called dark energy. Dark energy is a mysterious component of the universe that pushes space to expand faster. We don't know exactly what it is, but we can see its effect. The universe's expansion is accelerating. This acceleration is very gentle. It's not sudden. It's not dramatic. It's simply a gradual increase in the expansion rate, happening over billions of years. Eventually, in the far future, tens of billions of years from now, this acceleration will cause distant galaxies to move away so fast that their light will never reach us. They'll disappear from view, not because they're destroyed, but because space between us and them will be expanding faster than light can cross it. But that's unimaginably far in the future. For now, we can still see galaxies billions of light years away. We can still detect their light, stretched and reddened by expansion, but still arriving. We can still study the distant universe, still look back in time, still see how things were billions of years ago. All of this is delivered by light. Light traveling through expanding space, getting stretched by the expansion, but still carrying information, still arriving, still detectable. Light is our window into the cosmos, our connection to everything beyond our immediate environment. And it arrives constantly, steadily, peacefully, bringing news from across the universe, from across time. The stars you see at night are all part of this vast cosmic system. Each one is a sun, similar to our own, sitting at different distances, shining with its own light, existing in its own space. Some are older than our sun, some are younger, some are larger, some are smaller, some are hotter, some are cooler. Each one is unique, and yet all follow the same basic physical laws. Stars form from clouds of gas and dust in space. These clouds, called nebulae, are vast regions, light years across, where gas and dust collect. Gravity slowly pulls the gas and dust together into denser clumps. These clumps continue to collapse under their own gravity, getting denser and hotter as they collapse. Eventually, the center of a collapsing clump gets hot enough and dense enough for nuclear fusion to begin. When fusion starts, a star is born. This process takes millions of years. It's not sudden. It's not dramatic. It's a slow, gradual collapse, driven by gravity, accelerating over time, but still taking eons to complete. The gas cloud contracts, heats up, spins faster as it contracts, flattens into a disk, and finally, at the center, the temperature and pressure become high enough for fusion. Fusion is the process that powers stars. In the core of a star, hydrogen nuclei are crushed together by immense pressure and temperature until they fuse into helium nuclei. This fusion releases energy, a tremendous amount of energy, in the form of gamma rays. These gamma rays scatter through the star's interior, gradually working their way from the core to the surface, being absorbed and re-emitted countless times. This journey from core to surface takes thousands of years for the energy. By the time the energy reaches the star's surface, it is being converted into visible light and other wavelengths. This light then streams away from the star's surface into space, traveling at the speed of light, unimpeded, forever. The light we see from the sun is energy that was created by fusion in the sun's core thousands of years ago, slowly made its way to the surface, and then traveled 8 minutes through space to reach Earth. The sun fuses about 600 million tons of hydrogen into helium every second. This sounds like a lot, and it is. But the sun is so massive that it can continue this rate of fusion for billions of years without running out of fuel. The sun has enough hydrogen in its core to continue fusing for about another 5 billion years at the current rate. After that, it will begin fusing helium and will swell into a red giant star. But that's far in the future. For now, the sun burns steadily, peacefully, converting hydrogen to helium, releasing energy, maintaining the balance between gravity pulling inward and pressure pushing outward. This balance is perfect. The sun doesn't fluctuate wildly. It doesn't suddenly brighten or dim. It maintains a very stable output, varying by less than 1% over time. This stability has allowed life to evolve on Earth, relying on a steady source of light and heat from the sun. Other stars are similar. Each one maintains its own internal balance, fusing hydrogen into helium, releasing energy, shining steadily. The exact details vary with the star's mass. More massive stars burn hotter and faster, running through their fuel in millions of years rather than billions. Less massive stars burn cooler and slower, able to last for tens of billions of years or even trillions of years. The least massive stars, called red dwarfs, are so small and cool that they burn their hydrogen extremely slowly. A red dwarf star can live for trillions of years, far longer than the current age of the universe. Not a single red dwarf star has ever died yet, because the universe isn't old enough. Every red dwarf ever formed is still shining, still fusing hydrogen, still maintaining its steady balance. These red dwarfs are the most common type of star in the galaxy. About 3/4 of all stars are red dwarfs. They're too dim to see with the naked eye, even the closest ones. But they're out there in vast numbers, each one shining faintly, each one destined to shine for trillions of years before finally running out of fuel. Stars larger than the Sun have shorter lives, but more dramatic ends. When a massive star runs out of hydrogen in its core, it begins fusing heavier elements. Helium fuses into carbon and oxygen. Carbon and oxygen fuse into even heavier elements. Each stage of fusion produces less energy than the previous stage, and each stage happens faster. The star's core contracts and heats up with each new stage, while its outer layers expand, turning the star into a supergiant. Eventually, a massive star builds up an iron core. Iron cannot be fused to release energy. Once iron forms in the core, fusion stops. With no energy being released to counteract gravity, the core collapses catastrophically in a fraction of a second. This collapse creates a supernova explosion, one of the most energetic events in the universe. The outer layers of the star are blown away into space at tremendous speed, and the core collapses into either a neutron star or a black hole. Even these violent events, though, unfold according to physical laws, predictably, following the logic of gravity and nuclear physics. Supernovae don't happen randomly. They happen when massive stars reach the end of their lives, when they've exhausted all possible fusion reactions, when gravity finally overcomes all other forces. It's inevitable, determined by the star's mass and composition, happening at a specific point in the star's evolution. The light from a supernova travels outward into space, carrying the news of the star's death. This light can briefly outshine entire galaxies, visible across millions or billions of light years. And then it fades over weeks or months as the ejected material expands and cools. What's left behind is a rapidly expanding cloud of gas, enriched with heavy elements created in the star and in the supernova explosion itself. These heavy elements, including carbon, oxygen, nitrogen, iron, and many others, are essential for life as we know it. Every atom of carbon in your body, every atom of oxygen, every atom of iron in your blood was created inside a star and released into space when that star died. We are, quite literally, made of stardust, assembled from atoms that once existed in the core of ancient stars, released into space, incorporated into gas clouds, eventually forming our sun and planets, and finally becoming part of living things. This process has been happening for billions of years. The first stars in the universe contained only hydrogen and helium, the elements created in the Big Bang. When these stars died, they released the first heavy elements into space. Later generations of stars formed from gas enriched with these heavy elements, and when they died, they added even more. Generation after generation of stars, each one creating heavy elements, each one releasing those elements into space when it dies, gradually enriching the galaxy with the building blocks of planets and life. Our sun is a third-generation star, perhaps even later. It formed from a gas cloud that already contained small amounts of heavy elements from previous generations of stars. This allowed rocky planets like Earth to form, built from those heavy elements. Without previous generations of stars living and dying, there would be no Earth, no planets, no life. So, when you look at stars at night, you're seeing factories of element creation. Each star is fusing light elements into heavier ones. Each star will eventually die and release those elements into space. And future generations of stars and planets will form from that enriched material, continuing the cycle. This has been happening since the first stars formed, about 100 to 200 million years after the Big Bang. And it will continue happening for trillions of years into the future, as long as there's hydrogen gas to form new stars. The galaxy is slowly converting hydrogen into heavier elements, one star at a time, one generation at a time. This process is slow, taking billions of years, but it's inevitable. Eventually, Far in the future, the galaxy will run out of hydrogen gas. Star formation will cease. The last stars will burn out, and the galaxy will go dark, filled only with stellar remnants, white dwarfs, neutron stars, black holes, and planets drifting in the darkness. But that's trillions of years away. For now, stars continue forming, continue shining, continue enriching the galaxy with heavy elements. The cycle continues, peaceful and steady, driven by gravity and nuclear physics, creating the cosmic environment that makes life possible. Let's return to thinking about light itself, traveling through space. Every photon that reaches your eye from a distant star has traveled unimaginable distances without being absorbed, without being scattered, without being stopped. It passed through gas clouds, through the space between star systems, through the space between spiral arms of the galaxy, across light years of emptiness, until it finally reached Earth's atmosphere, passed through the atmosphere, and entered your eye. The probability of any single photon making that journey is remarkably low. Most photons from stars travel in directions where they'll never encounter anything. They'll simply continue traveling forever, or until the expansion of the universe stretches their wavelength to essentially zero energy. But some photons, a tiny fraction, happen to travel in exactly the right direction to reach Earth, to reach your location, to reach your eye. And when they do, you see a star. Each star visible in the night sky is sending photons in all directions. A tiny, tiny fraction of those photons happen to be traveling in Earth's direction. An even tinier fraction happen to reach your specific location on Earth. And an even tinier fraction happen to enter your eye. The fact that you can see thousands of stars means that billions upon billions of photons from those stars are arriving at Earth every second. And millions are entering your eyes every second when you look up. The stars you can see aren't even the nearest stars in most cases. The brightest stars visible are often distant but intrinsically very luminous stars, pouring out enormous amounts of light. Some are hundreds or even thousands of light years away, but still visible because they're so bright. Meanwhile, many nearby stars are too dim to see without a telescope, red dwarfs, and other faint stars that make up the majority of stellar neighbors. Proxima Centauri, our nearest stellar neighbor, is invisible to the naked eye despite being only 4.2 light years away. It's a red dwarf, too dim and cool to be seen without a telescope. Most stars in our immediate neighborhood are similar, small and dim. The stars you see when you look up are a biased sample, favoring the brightest stars rather than the nearest or most common stars. This means our visual impression of the night sky is quite different from the reality of stellar populations. We see a sky full of bright stars, and we might imagine the galaxy is full of such stars. But actually, the galaxy is dominated by small, dim red dwarfs, with bright stars being relatively rare. Our view is skewed toward the exceptional rather than the typical. Still, even the skewed view shows us something beautiful and calming. Thousands of points of light, each one a sun, each one pouring out energy into space, each one existing in its own neighborhood of the galaxy, separated from its neighbors by vast distances, shining independently, steadily, quietly. The night sky is a map of distant suns, each one located at a different distance and direction from Earth. Each one sending light our way, each one visible because we happen to be in the right place to intercept some of its light. The positions of stars in the night sky change very slowly over time. Stars move through the galaxy at their own speeds, in their own directions. This motion is called proper motion. For most stars, proper motion is extremely small from our perspective because the stars are so distant. Even though stars might be moving at tens or hundreds of kilometers per second through space, they're so far away that this motion only changes their position in the sky by tiny amounts over human lifetimes. Over thousands of years, proper motion becomes noticeable. The constellations we see today look slightly different from the constellations seen by ancient civilizations thousands of years ago. And thousands of years in the future, they'll look different again. But the changes are gradual, peaceful, predictable. We can calculate exactly where each star will be in the sky at any future date, based on its distance, velocity, and direction of motion. Some stars are moving toward us through space. Their light is blue-shifted, compressed to slightly shorter wavelengths by the Doppler effect. Other stars are moving away from us. Their light is red-shifted, stretched to slightly longer wavelengths. Most stars show small Doppler shifts, indicating modest velocities relative to us. A few show larger shifts, indicating higher velocities. By measuring these shifts, astronomers can map out how stars are moving through the galaxy, building a three-dimensional picture of stellar motion. The Sun itself is moving through the galaxy, orbiting the galactic center as discussed earlier, but it's also moving relative to nearby stars. The Sun is moving toward a point in the constellation Hercules at about 20 kilometers per second. This is the Sun's motion through what's called the local standard of rest, the average motion of stars in our neighborhood of the galaxy. Nearby stars have their own motions relative to this standard of rest, creating a complex pattern of stellar velocities. All of this motion is smooth, continuous, predictable. Stars don't suddenly change direction. They don't speed up or slow down randomly. They follow orbital paths determined by gravity, moving steadily along those paths over millions and billions of years. The galaxy is a system in motion, but it's orderly motion, governed by gravity, predictable and calm. When you look at the night sky, you're seeing a snapshot of this motion, frozen by the vast distances and slow timescales involved. The stars appear fixed in place, unchanging, eternal. And on human timescales, they essentially are. The night sky our ancestors saw thousands of years ago is almost identical to the one we see today. And the night sky thousands of years in the future will be almost identical to today's. The changes happen, but they happen slowly, too slowly to notice in a single lifetime. This constancy is comforting. The stars provide a reliable reference, unchanging over human timescales, a constant presence in the night sky generation after generation. Ancient navigators used stars to guide their journeys across oceans. Ancient peoples used stars to mark the seasons, to create calendars, to tell time at night. And we can still use stars for the same purposes today, because they're still in essentially the same places, still rising and setting at the same times of year, still following predictable patterns across the sky. The predictability of stellar motion reflects the orderly nature of gravity. Gravity is a simple force, always attractive, always proportional to mass, and inversely proportional to the square of distance. This simplicity leads to complex but predictable behavior. Planets orbit stars in ellipses. Stars orbit galactic centers in complex paths determined by the distribution of mass in the galaxy. Galaxies orbit each other in clusters. Everything moves according to gravity, and gravity is perfectly predictable, given enough information about masses and positions. This means the universe is, at a fundamental level, orderly and predictable. There's no chaos at the largest scales, no randomness, just matter moving according to gravity, light traveling according to the laws of electromagnetism, and everything unfolding according to physical law. This orderliness is deeply calming. The universe isn't arbitrary. It's not random. It's structured, predictable, following rules that we can understand. When you look at stars, you're seeing this orderliness in action. Each star exists where it does because of the gravitational forces that formed it and that govern its motion. Each star shines because of nuclear fusion, following the laws of nuclear physics. Each star sends light traveling through space, According to the laws of electromagnetism, everything happens for understandable reasons, following predictable patterns, creating a cosmos that is vast but comprehensible. The light reaching us from stars carries information. By analyzing starlight carefully, astronomers can determine a star's temperature, composition, mass, size, age, velocity, rotation rate, and much more, all from light. By spreading starlight into a spectrum, separating it into different wavelengths, and studying which wavelengths are present and which are absorbed, astronomers can read the story of each star. Different elements absorb light at specific wavelengths. Hydrogen absorbs certain wavelengths. Helium absorbs different wavelengths. Iron, calcium, sodium, and every other element each absorb their own unique set of wavelengths. By looking at which wavelengths are missing from a star's spectrum, astronomers can tell which elements are present in the star's atmosphere. This is called spectroscopy, and it's one of the most powerful tools in astronomy. Spectroscopy reveals that all stars are made primarily of hydrogen and helium, with small amounts of heavier elements. This is true everywhere we look, throughout the galaxy, throughout other galaxies, across the universe. The composition is remarkably uniform, reflecting the fact that all stars form from similar material, enriched to varying degrees by previous generations of stars. The temperature of a star determines its color. Hot stars appear blue or white. Cool stars appear red or orange. Medium temperature stars like our Sun appear yellow or white. By measuring a star's color and spectrum, astronomers can determine its temperature precisely. And temperature, combined with the star's brightness, allows astronomers to calculate the star's size. All of this information comes from light, from the steady stream of photons arriving from distant stars. Each photon carries information encoded in its wavelength, its energy, its direction. By collecting and analyzing many photons, astronomers reconstruct the properties of the stars that emitted them. This process requires patience. Stars are faint, and collecting enough light to analyze requires large telescopes and long exposure times. But the information is there, encoded in the light, waiting to be read. Every star tells its story through the light it emits, and we can read that story if we're willing to look carefully enough. The same principles apply to galaxies. Galaxies are collections of billions or hundreds of billions of stars, plus gas and dust, all held together by gravity. The light from a galaxy is the combined light of all its stars. By analyzing that light, astronomers can learn about the galaxy's properties, its total mass, its star formation rate, its chemical composition, its distance, its velocity. Distant galaxies appear as faint smudges of light through telescopes, but that light has traveled for billions of years to reach us, carrying information about those galaxies as they were in the distant past. By studying the light from very distant galaxies, astronomers study how galaxies were forming and evolving billions of years ago in the early universe. The most distant galaxies we can observe appear as they were more than 13 billion years ago, when the universe was less than a billion years old. These ancient galaxies look different from nearby modern galaxies. They're smaller, more irregular, forming stars at prodigious rates. They represent an earlier stage of galaxy evolution, before galaxies had grown and settled into the structures we see nearby today. All of this history is visible through telescopes, encoded in light, arriving steadily from across space and time. The universe reveals itself through light, gradually, patiently, as we build larger telescopes and more sensitive detectors. Each improvement in technology reveals new details, new galaxies, new phenomena, expanding our understanding of the cosmos. And yet, despite all we've learned, the fundamental nature of the universe remains humbling and calming. It's vast beyond comprehension, ancient beyond imagination. filled with more stars than humans can count, more galaxies than we can easily conceptualize. And yet it's orderly, predictable, following simple physical laws everywhere. You don't need to understand all the details to appreciate the night sky. You can simply look up, see the stars, and know that each point of light represents something vast and distant. Each star is a sun. Each sun has been shining for millions or billions of years. Each sun will continue shining for millions or billions of years more. And the light from each sun has traveled across space, silently, peacefully, to reach your eyes tonight. That's remarkable enough just by itself. No complex understanding needed. Just the simple, profound fact that we can see distant suns, separated from us by distances we'll never cross, existing in times we can barely imagine, yet connected to us by light, by the steady stream of photons traveling through space, bridging the gulf between here and there, between now and then. As you rest, as you relax, as you drift towards sleep, you can hold this thought gently in mind. The universe is vast, ancient, and filled with light. Stars shine steadily in the darkness, separated by enormous distances, each one independent, yet part of a larger whole. Light travels through space, carrying information, connecting distant places, moving steadily and predictably according to natural law. There's no urgency in any of this, no pressure, no deadline. Stars will continue shining whether we observe them or not. Light will continue traveling whether we detect it or not. The universe unfolds according to its own timescale, measured in billions of years, utterly indifferent to human concerns, but not hostile, just neutral, just existing, just continuing. You can rest in this knowledge. The cosmos is reliable. It's been here far longer than humanity. It will be here far longer into the future. It requires nothing from you. It simply exists, vast and peaceful, filled with light and matter and energy, following the same physical laws everywhere, predictable and steady. Let that steadiness, that reliability, that vast indifference in the best sense, be a comfort. You are part of this cosmos, made of atoms created in stars, living on a planet orbiting a star, under a sky filled with other stars. You're connected to it all, part of the same physical universe, subject to the same laws, made of the same matter. And for now, you can simply exist, rest, relax, knowing that the universe continues around you, steady and reliable, requiring nothing, offering everything, simply being what it is. Vast, ancient, filled with light, beautiful in its simplicity and complexity both. The light from stars will continue arriving. Photons will continue streaming through space. The universe will continue expanding. Galaxies will continue orbiting. Stars will continue shining, all following the gentle, inexorable laws of physics, all unfolding as they have for billions of years, all continuing as they will for billions more. Rest easy in this knowledge. The cosmos is vast, but it's orderly. It's ancient, but it's patient. It's indifferent, but it's not hostile. It simply is, and that is enough. Let's continue gently exploring the nature of starlight and what it reveals. The spectrum of a star tells us more than just its composition and temperature. It also reveals how the star is moving. When a star moves toward us, the wavelengths of its light are compressed slightly, shifted toward the blue end of the spectrum. When a star moves away from us, the wavelengths are stretched, shifted toward the red end. This is the Doppler effect, the same phenomenon that changes the pitch of a siren as it passes you on the street. For stars, the Doppler shift is usually quite small. Most stars in our galaxy move at speeds of a few dozen kilometers per second relative to us, which produces only tiny shifts in wavelength. But these shifts are measurable with precise instruments, and they tell us about stellar motion, about how stars orbit the galaxy, about how binary star systems orbit each other. Binary stars are quite common. Many stars exist in pairs, two stars orbiting their common center of mass. Sometimes both stars are visible. Sometimes only one is visible, and we detect the companion by its gravitational influence on the visible star. Sometimes we detect both stars through spectroscopy, seeing two sets of spectral lines that shift back and forth as the stars orbit each other. These binary systems orbit peacefully, following the laws of gravity, year after year, century after century. Some binary stars orbit very close to each other, completing one orbit in days or even hours. Others orbit at great distances, taking centuries or millennia to complete a single orbit. Each system is stable, balanced, following its own rhythm determined by the masses of the stars and their separation. When two stars in a binary system are very close, interesting things can happen. If one star swells into a red giant, it might transfer some of its outer atmosphere to its companion. Gas flows from one star to the other, creating complex structures and sometimes brilliant outbursts of light. But even these dramatic events unfold according to physical law, predictably, following the logic of gravity and gas dynamics. Some binary systems contain a white dwarf, the dense remnant of a sun-like star that has exhausted its fuel. If the white dwarf has a companion star, it can pull gas from that companion onto its own surface. This gas accumulates, compressed and heated by the white dwarf's intense gravity. Eventually, the accumulated gas can ignite in a thermonuclear explosion called a nova. Novas are bright, but not as bright as supernovas. A nova occurs on the surface of a white dwarf, blowing away the accumulated gas, but leaving the white dwarf intact. The white dwarf then begins accumulating gas again, and the process can repeat. Some nova systems erupt regularly, every few years or decades, each eruption predictable and similar to the last. Even more dramatic are Type Ia supernovas, which also occur in binary systems with white dwarfs. If a white dwarf accumulates enough mass from its companion, it can exceed a critical limit called the Chandrasekhar limit, about 1.4 times the mass of the Sun. Above this limit, the white dwarf becomes unstable and collapses catastrophically, triggering a complete thermonuclear explosion that destroys the white dwarf entirely. Type Ia supernovas are important in astronomy because they're remarkably consistent in brightness. Every Type Ia supernova reaches approximately the same peak brightness because they all result from white dwarfs exploding at the same critical mass. This makes them useful as centered candles for measuring distances across the universe. By comparing a Type Ia supernova's apparent brightness to its known actual brightness, astronomers can calculate its distance. Using Type Ia supernovas, astronomers discovered that the universe's expansion is accelerating. In the late 1990s, two teams of astronomers studied distant Type Ia supernovas and found they were fainter than expected, which meant they were farther away than expected. This implied the universe had expanded faster than anticipated, which meant the expansion was accelerating. This discovery led to the realization that dark energy exists and dominates the universe's energy budget. All of this knowledge came from studying light, from analyzing the brightness and spectra of distant supernovas, from patient observation and careful measurement, from collecting photons that had traveled billions of light years to reach our telescopes, carrying information about events that happened long ago in distant galaxies. The light from these supernovas traveled through expanding space, getting stretched and dimmed by the expansion, but still carrying measurable information, still arriving in sufficient quantity to be detected and analyzed, still revealing secrets about the universe's structure and evolution. This is the power of light as a messenger. It carries information faithfully across enormous distances and timescales. A photon emitted by a supernova explosion 10 billion years ago still carries information about that explosion when it reaches us today. The photon hasn't changed. The information is preserved. We can read it if we know how to look. Different types of stars emit different amounts and colors of light. The hottest, most massive stars shine brilliant blue-white, pouring out tremendous amounts of ultraviolet and visible light. These stars burn through their fuel quickly, living only millions of years before exploding as supernovas. Despite their short lives, they're incredibly luminous while they exist, visible across vast distances. Medium-mass stars like our Sun shine yellow or white, with moderate luminosity and moderate lifetimes measured in billions of years. They're stable, reliable, long-lived. They form the backbone of stellar populations, neither the most common nor the most rare, but important nonetheless. Low-mass stars, the red dwarfs, shine dim red or orange, barely luminous at all by stellar standards. But they're incredibly numerous, making up 3/4 of all stars, and incredibly long-lived, burning for trillions of years. They represent the future of the galaxy. Long after all the massive stars have died, long after all the sun-like stars have died, the red dwarfs will still be shining. Dim and cool, but still alive, still fusing hydrogen, still maintaining their internal balance. The galaxy contains all these types of stars in various proportions. The massive stars are rare but eye-catching. The medium stars are less common than red dwarfs, but more visible. The red dwarfs are everywhere, but invisible to the naked eye. Together, they create a stellar population that has been evolving for billions of years, with new stars forming and old stars dying in a continuous cycle. Star formation happens in regions called molecular clouds, vast accumulations of gas and dust where gravity can pull material together into dense cores that eventually collapse to form stars. These clouds are cold, just a few degrees above absolute zero in most regions, and they're mostly invisible in visible light because dust blocks the light. But in infrared wavelengths, we can see through the dust and observe star formation in progress. Infrared telescopes reveal dense cores inside molecular clouds, regions where gas is collapsing, heating up, beginning the long process of becoming stars. We can see protostars, objects that have accumulated enough mass to be warm and bright in infrared light, but haven't yet started fusion. We can see young stars still surrounded by disks of gas and dust, material left over from the star's formation that might eventually form planets. These observations show that star formation is happening right now in our galaxy and in galaxies across the universe. New stars are being born constantly, replacing stars that die, maintaining the galaxy's stellar population. The rate of star formation varies from galaxy to galaxy and has changed over cosmic time, but it continues, driven by gravity, turning cold gas into hot stars. Our own sun formed about 4.6 billion years ago from a collapsing cloud of gas and dust. That cloud was enriched with heavy elements from previous generations of stars, allowing rocky planets to form. The cloud collapsed, flattened into a disk, and at the center, our sun ignited. Around it, in the disk, dust grains stuck together, building up into pebbles, then boulders, then planetesimals, and finally planets. This process took millions of years. It wasn't sudden. Gravity slowly accumulated material, building larger and larger objects. The inner solar system formed rocky planets like Earth because it was too warm for ices to condense. The outer solar system formed gas and ice giant planets because it was cold enough for ices to exist, providing more material to build large planets. Eventually, the solar system settled into its current configuration. 4 rocky inner planets, a belt of asteroids, 4 giant outer planets, and beyond them, a region of icy bodies including Pluto and countless similar objects. All of this orbits the Sun, held in place by the Sun's gravity, stable and predictable, following the same orbital paths year after year, with only tiny variations. The Sun's light illuminates this entire system. Every planet receives sunlight, though the amount varies greatly with distance. Mercury receives intense sunlight, made by proximity to the Sun. Earth receives moderate sunlight, perfect for liquid water and life. Neptune receives dim sunlight, barely enough to warm the planet above the cold of space. But all receive sunlight, and that light has been arriving steadily for billions of years. The planets don't produce their own light. They shine by reflecting sunlight. When you see Venus in the evening sky, you're seeing sunlight bouncing off Venus's clouds. When you see Mars, you're seeing sunlight reflecting from Mars's rusty surface. When you see Jupiter, you're seeing sunlight reflecting from Jupiter's cloud tops. This reflected light is much fainter than the Sun's direct light, but still bright enough to be easily visible. The inner planets can appear quite bright because they're close to both the Sun and Earth. Venus, in particular, can be the brightest object in the sky after the Sun and Moon. Brilliant in the evening or morning sky, easily visible even in twilight. The outer planets are dimmer because they're farther from the Sun, receiving less sunlight to reflect, and farther from Earth, appearing smaller and fainter, but they're still visible with the naked eye. Jupiter, Saturn, Mars, Venus, and Mercury have been observed since ancient times, recognized as wandering stars that move against the background of fixed stars, following predictable paths across the sky. These planets follow elliptical orbits around the Sun, as described by Kepler's laws. Each orbit is an ellipse with the Sun at one focus. Each planet moves faster when closer to the Sun and slower when farther away. The time it takes to complete one orbit depends on the planet's distance from the Sun, with more distant planets taking longer to orbit. Earth takes 1 year to orbit the Sun. Mars takes about 1.9 years. Jupiter takes about 12 years. Saturn takes about 29 years. Neptune takes about 165 years. Each planet follows its own rhythm, its own schedule, never deviating, never varying except by tiny amounts. This regularity allows us to predict planetary positions centuries into the future or past, calculating exactly where each planet will be in the sky on any given date. This predictability reflects the orderly nature of gravity once again. The planets aren't random. They're not chaotic. They follow precise mathematical laws, discoverable through observation and describable through equations. Newton's law of universal gravitation explains planetary motion perfectly for most purposes. Einstein's general relativity adds small corrections that become important for extremely precise measurements. But the basic picture is the same. Gravity creates orderly, predictable motion. The same laws that govern planets also govern moons, asteroids, comets, and every other object in the solar system. Everything orbits according to gravity, following elliptical or hyperbolic paths depending on the object's velocity and distance from the Sun. Some objects, like planets and asteroids, follow stable orbits that have remained essentially unchanged for billions of years. Others, like comets, follow highly elongated ellipses that bring them close to the Sun at one end of their orbit and send them far into the outer solar system at the other end. Comets are icy bodies, remnants from the formation of the solar system, preserved in the cold outer reaches of the solar system for billions of years. When a comet's orbit brings it close to the Sun, solar heating vaporizes some of the ice, creating a glowing atmosphere around the comet called a coma, and often a tail pointing away from the Sun, pushed by solar radiation and the solar wind. Comets can be spectacular, with tails stretching millions of kilometers across space. But even these dramatic objects follow predictable orbits, returning to the inner solar system on regular schedules. Halley's Comet, the most famous periodic comet, returns every 76 years. It's been observed and recorded for over 2,000 years, appearing on schedule throughout human history. Last visible in 1986 and due to return in 2061. Each appearance of Halley's Comet is slightly different because the comet loses some of its ice with each pass near the Sun, gradually changing over time. But the orbit remains predictable, calculable, following the same gravitational laws as everything else in the solar system. The solar system is a small, stable system embedded in a vast galaxy. The Sun and its planets occupy a tiny region of space, insignificant on galactic scales, yet complex and interesting in their own right. 8 planets, hundreds of moons, millions of asteroids, billions of comets, all orbiting the Sun, all following predictable paths, all existing in relative harmony for billions of years. This stability is remarkable when you consider the violence of the solar system's early history. The planets formed through countless collisions between smaller bodies. Planetesimals crashed into each other, sticking together, building up mass. Larger collisions happened too, including one that likely created Earth's moon when a Mars-sized object struck the early Earth, blasting material into orbit that later accumulated into the moon. Despite this violent beginning, the solar system settled into stability. The planets found their orbits, cleared their neighborhoods of smaller debris, and achieved a stable configuration that has lasted for over 4 billion years. The asteroid belt between Mars and Jupiter represents material that never accumulated into a planet, prevented from doing so by Jupiter's gravity. But even the asteroids follow stable, predictable orbits, most of them never threatening Earth or the other planets. Occasionally, gravitational interactions can send an asteroid on a path that crosses Earth's orbit. Very rarely, such an asteroid actually collides with Earth, creating an impact crater and, in the largest cases, causing mass extinctions. The impact that killed the dinosaurs 66 million years ago was one such event, a random collision that had profound effects on Earth's biosphere. But such impacts are extremely rare on human timescales. Most asteroids stay in their orbits, most comets stay in the outer solar system, and most of the time, Earth orbits peacefully through a solar system that is mostly empty space. The distances between objects are vast compared to their sizes. Space is an excellent name for what lies between planets. The light from the Sun takes different amounts of time to reach different planets. It takes about 8 minutes to reach Earth, as mentioned earlier. It takes about 3 minutes to reach Mercury, about 6 minutes to reach Venus, about 12 minutes to reach Mars, about 43 minutes to reach Jupiter, about 80 minutes to reach Saturn, about 5.5 hours to reach Neptune. This means when we observe the outer planets through telescopes, we're seeing them as they were hours ago. When space probes send signals from the outer solar system, those signals travel at the speed of light and take hours to reach Earth. The Voyager spacecraft, now beyond the orbit of Neptune, sends signals that take over 22 hours to reach Earth. We communicate with them in slow motion, sending a command and waiting nearly a full day for a response. Despite these light travel times, the solar system feels immediate to us because we live in it, because the timescales are manageable, because we can send spacecraft to explore the planets and receive data back within years or decades rather than centuries or millennia. The solar system is our cosmic neighborhood, the region of space we can interact with directly. Beyond the solar system lies interstellar space, the vast emptiness between stars. The nearest star system, Alpha Centauri, lies about 4.37 light-years away. This is about 277,000 times farther from the Sun than Earth is, or about 25 trillion miles, or 41 trillion kilometers. The distances become so large that they're difficult to visualize or comprehend. If you could travel at the speed of a typical spacecraft, say 40,000 miles per hour, it would take about 70,000 years to reach Alpha Centauri. No human spacecraft has ever traveled more than a tiny fraction of this distance from Earth. The Voyager probes, humanity's most distant emissaries, are currently about 15 billion miles from Earth, which sounds like a lot, but is only about 0.2% of the distance to Alpha Centauri. At the current rate, Voyager 1 would take about 75,000 years to travel a distance equal to that between the Sun and Alpha Centauri. And even then, it wouldn't arrive at Alpha Centauri because it's not headed in that direction. It's headed toward a different part of the galaxy, on a path that will take it nowhere near any star for hundreds of thousands of years. This illustrates the incredible isolation of stars. Even our nearest stellar neighbors are so distant that reaching them with current technology would take longer than human civilization has existed. The stars we see at night are islands, separated by oceans of space too vast to cross with any foreseeable technology. Light crosses these distances, but matter does not, at least not on human timescales. Light from Alpha Centauri reaches us in a little over 4 years. Light from the Sun will reach Alpha Centauri in a little over 4 years. But the two star systems remain isolated, separated by a distance that matter cannot easily cross. This isolation is true throughout the galaxy. Each star system is separated from its neighbors by light years of empty space. Most star systems will never be visited by travelers from other stars. Most will exist in isolation for their entire lives, shining alone in the darkness, unwitnessed except by the light they send out into space. And yet, despite this isolation, the galaxy is a connected system. Gravity connects everything. Every star in the galaxy pulls on every other star through gravity. The total gravitational field, all the galaxy stars, creates the structure we observe: the spiral arms, the central bulge, the flat disk. Everything is connected through gravity, even if nothing can travel between stars in less than thousands or millions of years. The galaxy rotates as a whole, but not like a solid disk. Different parts rotate at different speeds. The result is called differential rotation. Stars near the galactic center orbit faster than stars farther out. This differential rotation creates and maintains the spiral arm structure visible in many galaxies, including our own. Spiral arms are regions where stars are more densely packed than average. They're not permanent structures. Individual stars drift into and out of spiral arms as they orbit the galaxy. But the spiral pattern persists because new stars form in the spiral arms, creating bright blue stars that illuminate the arms. These bright stars don't live long, just a few million years, but they're constantly replaced by new star formation, keeping the spiral arms bright and visible. Our Sun has likely drifted into and out of spiral arms multiple times during its 4.6 billion year history. Currently, we're located between two major spiral arms, in a region sometimes called the Orion Spur or Orion Arm, a minor structure between the Sagittarius and Perseus arms. The Sun orbits the galaxy, taking about 230 million years per orbit, drifting through different regions, sometimes in denser areas, sometimes in sparser areas, always moving, always following its orbital path. The view of the night sky changes slowly as we orbit the galaxy. Stars that are currently nearby will eventually be left behind as we move ahead of them in our orbit or fall behind them. New stars will appear as we approach regions we've never been near before. But these changes happen so slowly that they're imperceptible on human timescales. Over millions of years, the night sky gradually changes. Over tens or hundreds of millions of years, it changes dramatically. But year to year, century to century, even millennium to millennium, The changes are minimal. This stability, this slow pace of change, this vast timescale is characteristic of the galaxy and the universe. Things change, but they change slowly. Stars form, stars die, galaxies evolve, the universe expands, but all of it happens on timescales that dwarf human lifetimes and human civilizations. A human life is a tiny fraction of a cosmic second. Human civilization is a brief moment in cosmic time. The entire history of life on Earth, nearly 4 billion years, is less than a third of the universe's age. And yet we can observe the universe, study it, understand it, see across billions of light years to the distant past, calculate the future evolution of stars and galaxies, comprehend the laws that govern everything. This ability to understand is itself remarkable. Conscious beings on a small planet, orbiting an ordinary star in an ordinary galaxy, can look out into space and decipher the universe's structure, history, and laws. We're made of matter from stars, organized in complex ways, capable of observing and understanding the cosmos that created us. The light that makes this understanding possible travels to us constantly. Every clear night, photons from countless stars enter our atmosphere, pass through the air, and arrive at the ground, available to be detected by eyes or telescopes. These photons carry information across vast distances, connecting us to places we'll never visit, times we'll never experience, phenomena we'll never witness directly. But through light, we can observe it all. Through spectroscopy, we can analyze it. Through physics, we can understand it. The universe reveals itself to those who look carefully, patiently, thoughtfully. And what it reveals is both humbling and comforting. Humbling in its vastness and age, comforting in its orderliness and predictability. You are part of this vast system, made of atoms forged in stars, living on a planet formed from stellar debris, warmed by the light of a star that has shone steadily for billions of years, surrounded by a galaxy containing hundreds of billions of other stars, most with their own planetary systems. Existing in a universe containing hundreds of billions of galaxies, each one a vast system of stars and gas and dark matter, and all of it follows natural laws. All of it is knowable, at least in principle. All of it connects together into one vast, coherent whole. You are not separate from the universe. You are part of it, made of it, existing within it, subject to the same laws as everything else. Let this knowledge be a comfort. The universe is vast, but it's not arbitrary. It's ancient, but it follows timeless laws. It's mostly empty space and dark matter, but it contains islands of complexity and beauty, including the island you inhabit. Stars will continue shining. Light will continue traveling. The universe will continue expanding and evolving. And all of it will happen whether you watch or not, whether you understand or not, whether you exist or not. The cosmos doesn't need you, but you are still part of it, still made of it, still connected to it through the simple fact of existence. Rest in this knowledge. Let the vastness be calming rather than frightening. Let the timescales be peaceful rather than oppressive. You exist for a brief moment in cosmic time, but you exist nonetheless, conscious and aware, able to observe and understand, able to appreciate the beauty and structure of the universe around you. The stars above you have shone for millions or billions of years. Their light has traveled across space to reach you. And for this moment, you can see them, appreciate them, understand something of what they are and how they work. That connection, through light, through understanding, is real and meaningful, even if temporary. Everything is temporary on some time scale. Stars eventually die. Galaxies eventually merge. Even the protons that make up atoms might eventually decay, given enough time. But for now, in this era of the universe, stars shine, galaxies rotate, light travels, and conscious beings can observe it all and find meaning and beauty in it. Let yourself relax into this reality. The universe is what it is. Vast, ancient, beautiful, orderly and different, but not hostile. It simply exists, and you exist within it, for a brief time, with the gift of awareness and understanding. The night sky is always there, patient and unchanging on human timescales, offering connection to something larger than yourself, larger than humanity, larger than Earth. The stars are always shining, always sending light, always there, reliable and constant. And that light will continue to arrive night after night, carrying the same message it has carried for billions of years. The universe exists. It is vast, it is beautiful, and it follows comprehensible laws. You can observe it, study it, appreciate it, find peace in it. Rest now, knowing that the cosmos continues around you, steady and reliable, requiring nothing from you, offering everything to those who look, existing as it has for billions of years, existing as it will for billions more, unchanged in its fundamental nature, eternal in its physical laws, beautiful in its simplicity and complexity both. The gentle light of distant stars will continue to fall on Earth, silent and patient, connecting us to the vast universe beyond our small world, reminding us that we are part of something much larger, something ancient and enduring, something worth contemplating, something profoundly calming in its constancy and its indifference, its beauty and its truth. The silent formation of worlds. Let's turn our attention now from the stars themselves to what forms around them. The planets, moons, and smaller bodies that populate solar systems throughout the galaxy. These worlds form quietly, gradually, over millions of years, following patterns determined by gravity, temperature, and the chemistry of the materials available in each star system. Planet formation is not a violent process, despite involving countless collisions. It's a patient accumulation of matter, starting from microscopic dust grains and building up, piece by piece, collision by collision, into objects thousands of kilometers across. The process takes time, but time is abundant in the universe. Millions of years pass easily when gravity is doing the work. When a star forms from a collapsing cloud of gas and dust, not all the material falls into the star itself. Some remains in orbit around the young star, forming a disk. This disk is called a protoplanetary disk, and it's where planets form. The disk is made primarily of hydrogen and helium gas, the most abundant elements in the universe, along with small amounts of heavier elements and dust grains. These dust grains are tiny, typically less than a micrometer across, smaller than the width of a human hair. They're made of various materials depending on the temperature. Close to the star, where it's hot, only materials like iron and rock can condense into solid form. Farther from the star, where it's cooler, ices can also form: water ice, methane ice, ammonia ice, carbon dioxide ice. This temperature gradient creates different conditions at different distances from the star, which is why rocky planets form close to stars and gas giant planets form farther out. The inner region doesn't have enough solid material to build very large planets. The outer region has both rock and ice, providing more building material, allowing larger planets to form. The dust grains in the protoplanetary disk orbit the young star, colliding with each other occasionally. When two dust grains collide gently, they can stick together through molecular forces, electrostatic attraction, or simply by tangling with each other if they have irregular shapes. This creates a slightly larger grain, which then continues orbiting, occasionally colliding and sticking to other grains. This process happens throughout the disk, everywhere at once. Dust grains stick together, forming larger grains. These larger grains stick together, forming pebbles. The pebbles stick together, forming rocks. The rocks stick together, forming boulders. Each step happens slowly, through countless gentle collisions, accumulating mass grain by grain. As objects grow larger, gravity becomes important. A boulder-sized object doesn't have much gravity, but it has some. A mountain-sized object has more gravity. A kilometer-sized object has enough gravity to noticeably attract nearby objects. This gravitational attraction speeds up the growth process. Instead of relying on random collisions, larger objects can gravitationally pull in nearby material, sweeping up everything in their orbital path. These growing objects are called planetesimals. They range from kilometers to hundreds of kilometers across. They're too small to be spherical. Gravity isn't strong enough yet to pull them into round shapes. They're irregularly shaped, like large asteroids, tumbling through space as they orbit the star, occasionally colliding with other planetesimals. When two planetesimals collide, the outcome depends on their relative speed. If they collide gently, they can stick together, merging into a larger object. If they collide too fast, they can shatter, breaking into many smaller pieces. The debris from such collisions can later reaccumulate, or it can be swept up by other planetesimals. Either way, the general trend is toward accumulation, toward building larger and larger objects. This process is called accretion, and it's the fundamental mechanism of planet formation. Small objects accumulate into larger objects through gravity and collisions. The process is slow but inexorable. Over hundreds of thousands of years, planetesimals grow into objects hundreds of kilometers across. Over millions of years, they grow into objects thousands of kilometers across. Planetary embryos, protoplanets, objects large enough that their gravity pulls them into spherical shapes. At this stage, the young solar system contains many protoplanets, perhaps dozens or hundreds, all orbiting the star in the same direction, all jostling for space, all continuing to grow by accumulating smaller objects. The protoplanet's gravity begins to dominate their regions of the disk. Each one clears a path through the disk, sweeping up material in its orbit, growing larger as it does so. But there are too many protoplanets to all survive. Their orbits aren't stable with so many large objects so close together. Gravitational interactions between protoplanets gradually change their orbits. Some move inward toward the star, others move outward, and inevitably, some collide. Collisions between protoplanets are enormous events, releasing tremendous energy. When two Mars-sized objects collide, the impact vaporizes rock, creates huge amounts of heat, and can blast material into space. These are the largest collisions in the planet formation process, and they determine the final architecture of the planetary system. Earth's moon likely formed from such a collision. Early in Earth's history, a Mars-sized protoplanet called Theia struck the young Earth at an oblique angle. The impact vaporized much of both objects, creating a huge cloud of vapor and debris around Earth. This debris quickly reaccumulated in orbit around Earth, forming the Moon within a few thousand years of the impact. The Moon has been orbiting Earth ever since, about 4.5 billion years. It formed close to Earth, perhaps only a few Earth radii away, and has been gradually moving farther away over time due to tidal interactions. Currently, the Moon orbits at about 384,000 kilometers from Earth, and it continues to recede at about 3.8 centimeters per year. This is a tiny amount, imperceptible on human timescales, but over billions of years, it adds up to significant distance. The Moon's orbit is not perfectly circular. It's slightly elliptical, so the Moon's distance from Earth varies between about 356,000 kilometers at closest approach, perigee, and about 406,000 kilometers at farthest distance, apogee. This variation is predictable and regular, repeating every 27.3 days, which is the Moon's orbital period. The moon always shows the same face to Earth. This is called synchronous rotation or tidal locking. The moon rotates on its axis once every 27.3 days, which is exactly the same as its orbital period. So the same side always faces Earth. This happened because Earth's gravity created tidal forces in the moon early in its history, when the moon was closer and the forces were stronger. These tidal forces gradually slowed the moon's rotation until it became locked in synchronous rotation. Most large moons in the solar system are tidally locked to their planets. Jupiter's 4 large moons, Saturn's, Titan, and many other moons all show the same face to their parent planets. It's a natural outcome of tidal forces acting over long periods of time. The process is slow but inevitable for moons orbiting close to their planets. Tidal forces are caused by the difference in gravitational pull across an object. The side of the moon facing Earth feels slightly stronger gravity than the center of the moon, and the center feels slightly stronger gravity than the far side. This difference creates a stretching force, pulling the moon into a slightly elongated shape. The same thing happens to Earth due to the moon's gravity, creating the ocean tides we observe. Ocean tides rise and fall twice per day as Earth rotates beneath the tidal bulges created by the moon's gravity. The sun also creates tidal forces on Earth, about half as strong as the moon's. When the sun and moon align at new moon and full moon, their tidal forces add together, creating larger tides called spring tides. When they're at right angles at first quarter and third quarter moon, their tidal forces partially cancel, creating smaller tides called neap tides. These tidal patterns have repeated every day for billions of years, regular and predictable, driven by the orbital motions of Earth and Moon around each other and around the Sun. The tides don't change in any significant way from year to year. They follow the same pattern, governed by the same gravitational forces, creating the same rise and fall of ocean waters. The moon's influence on Earth extends beyond tides. The moon stabilizes Earth's axial tilt, preventing it from varying widely over time. Earth's axis is currently tilted about 23.5 degrees relative to its orbital plane around the Sun. This tilt is responsible for the seasons. Summer occurs when your hemisphere is tilted toward the Sun. Winter when it's tilted away. Without the moon, Earth's axial tilt would vary chaotically over millions of years due to gravitational influences from other planets. The tilt could change from nearly 0 degrees to 85 degrees or more, creating extreme climate variations. But the moon's gravity keeps Earth's tilt relatively stable, varying only between about 22 and 24.5 degrees over a 41,000-year cycle. This stability has been important for Earth's climate and possibly for the evolution of life. Mars, which has 2 tiny moons but no large moon like Earth's, those experience large variations in axial tilt over millions of years. Mars's tilt has varied between about 15 degrees and 35 degrees, and possibly even more extreme values in the distant past. These changes have dramatic effects on Mars's climate, redistributing ice between the poles and mid-latitudes, changing atmospheric pressure, creating very different conditions at different times in Mars's history. Venus rotates very slowly and in the opposite direction from most planets. One day on Venus, one rotation on its axis, takes about 243 Earth days, which is actually longer than Venus's year, one orbit around the Sun, which takes about 225 Earth days. This means the Sun rises in the west and sets in the east on Venus, and a solar day, sunrise to sunrise, takes about 117 Earth days. We don't know exactly why Venus rotates this way. It might have been struck by a large object early in its history, knocking it into retrograde rotation, or tidal forces from the Sun, combined with Venus's thick atmosphere, might have gradually slowed and reversed its rotation over billions of years. Either way, Venus now rotates slowly backward, creating a very different day-night cycle from Earth's. Mercury also has an unusual rotation. It rotates 3 times for every 2 orbits around the Sun, a 3-to-2 spin orbit resonance. This means Mercury's day is exactly 2/3 as long as its year. This resonance was created by the Sun's tidal forces acting on Mercury over billions of years. Mercury's orbit is quite elliptical, and the resonance is stable because of the specific combination of Mercury's orbital period, orbital eccentricity, and the Sun's tidal forces. These rotational patterns show how planetary systems evolve over long timescales. Rotation rates change due to tidal forces. Orbits gradually shift due to gravitational interactions. Everything slowly evolves toward more stable configurations. The solar system we see today is the result of 4.6 billion years of this gradual evolution, settling into a configuration that is relatively stable and will remain so for billions of years to come. The gas giant planets, Jupiter, Saturn, Uranus, and Neptune, formed differently from the rocky planets. They formed farther from the Sun, where temperatures were cold enough for ices to condense. This provided much more solid material, allowing these planets to grow much larger. The process started the same way, with dust and ice grains accumulating into larger objects. But in the outer solar system, there was enough material to build very large planetary cores, 10 or 20 times Earth's mass. Once a core became this large, its gravity was strong enough to capture gas directly from the protoplanetary disk. Hydrogen and helium gas fell onto the core, accumulating into a thick atmosphere, which kept growing as the planet's gravity pulled in more and more gas. Jupiter and Saturn captured enormous amounts of gas, becoming much more massive than their original cores. Jupiter is now about 318 times Earth's mass, and Saturn is about 95 times Earth's mass. Most of this mass is hydrogen and helium, with only a small, rocky, icy core at the center. These planets are essentially small stars, but didn't accumulate enough mass to start fusion. They're mostly gas, with no solid surface to stand on. Uranus and Neptune also captured gas, but less than Jupiter and Saturn. They're called ice giants rather than gas giants because they contain larger proportions of ices, water, methane, ammonia, relative to hydrogen and helium. They're each about 15 to 17 times Earth's mass, smaller than Jupiter and Saturn, but still much larger than Earth. All 4 giant planets have ring systems, though Saturn's rings are by far the most spectacular. Saturn's rings are made of countless particles of ice and rock, ranging from grain-sized to house-sized, all orbiting Saturn in a thin disk. The rings are very wide, extending hundreds of thousands of kilometers from Saturn, but they're remarkably thin, only about 10 meters thick in most places. The rings formed from a moon or comet that ventured too close to Saturn and was torn apart by tidal forces. When an object gets too close to a planet, the planet's tidal forces can overcome the object's own gravity, pulling it apart into fragments. These fragments then spread out into a ring around the planet. The distance at which this happens is called the Roche limit, and it varies depending on the planet's mass and the object's composition. Saturn's rings are not permanent. The ring particles gradually spiral inward due to drag from Saturn's tenuous upper atmosphere and electromagnetic effects. Current estimates suggest Saturn's rings might disappear in about 100 million years. This is a short time compared to the age of the solar system, which suggests the rings are relatively young, perhaps only a few 100 million years old. Jupiter's rings are much fainter than Saturn's, barely visible even through powerful telescopes. They're made of dust particles knocked off Jupiter's inner moons by micrometeorite impacts. These dust particles quickly spiral into Jupiter, so the rings are constantly being replenished by new impacts on the moons. Uranus and Neptune also have faint ring systems, discovered relatively recently through spacecraft observations. These rings are dark and narrow, made of dust and small rocks, probably similar in origin to Jupiter's rings. All 4 giant planets have many moons. Jupiter has 95 known moons. Saturn has 146. Uranus has 28. And Neptune has 16. These numbers continue to increase as smaller moons are discovered through improving telescope technology. Most of these moons are very small, just a few kilometers across, probably captured asteroids or comets rather than moons that formed along with the planet. But each giant planet also has several large moons that did form along with the planet, from the same disk of material that surrounded the planet as it formed. These large moons orbit in the planet's equatorial plane, in the same direction the planet rotates, just like planets orbit the Sun. They're regular satellites, following predictable patterns. Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, were discovered by Galileo in 1610 and are called the Galilean moons. They're large enough to be visible through small telescopes, appearing as tiny points of light near Jupiter, changing position from night to night as they orbit. Io is the innermost Galilean moon, orbiting very close to Jupiter. It is the most volcanically active body in the solar system, with hundreds of active volcanoes covering its surface. This volcanic activity is driven by tidal heating. Jupiter's gravity creates strong tidal forces in Io, and Io's orbit is slightly elliptical due to gravitational interactions with the other Galilean moons. So the tidal forces vary as Io orbits. This varying stress heats Io's interior, keeping it molten and driving intense volcanic activity. Europa, the next moon out, is covered in smooth ice. Its surface has very few impact craters, suggesting the ice is young, constantly being renewed from below. Beneath the ice, there's almost certainly a liquid water ocean, kept warm by tidal heating similar to Io's, but not as intense. This ocean might be tens of kilometers deep, containing more liquid water than all of Earth's oceans combined. Europa is one of the most promising places in the solar system to search for life beyond Earth. Ganymede is the largest moon in the solar system, even larger than the planet Mercury. It has its own magnetic field, unique among moons, suggesting a liquid iron core. Its surface is a mix of old, dark, cratered terrain and younger, brighter grooved terrain. Like Europa, Ganymede probably has a subsurface ocean beneath its icy crust. Callisto is the outermost Galilean moon, heavily cratered, apparently unchanged for billions of years. It orbits far enough from Jupiter that tidal heating is minimal. So unlike Io, Europa, and Ganymede, Callisto appears to be a cold, dead world with no internal activity. But even Callisto might have a subsurface ocean, kept liquid by heat from radioactive decay in its interior. Saturn's largest moon, Titan, is bigger than Mercury and has a thick atmosphere, the only moon in the solar system with a substantial atmosphere. Titan's atmosphere is mostly nitrogen, similar to Earth's, but much denser. The surface pressure on Titan is about 1.5 times Earth's sea level pressure. The atmosphere is so thick and hazy that the surface is completely obscured in visible light. Titan has lakes and seas of liquid methane and ethane on its surface, particularly near the poles. These are the only stable bodies of liquid on any world surface besides Earth. Titan has a methane cycle similar to Earth's water cycle, with methane rain, rivers, lakes, and evaporation. Clouds of methane form in the atmosphere and rain methane onto the surface, which flows into rivers and lakes, eventually evaporating back into the atmosphere to complete the cycle. The temperature on Titan's surface is about -179 degrees Celsius, cold enough that water ice is as hard as rock and methane can exist as a liquid. Titan's surface is a frozen landscape of water ice mountains and methane lakes, shaped by processes similar to those on Earth, but using different materials. Titan might have a subsurface ocean of liquid water beneath its icy crust, like Europa and Ganymede, and the combination of organic molecules, liquid water, and energy sources makes Titan another promising place to search for life. Though any life there would be very different from Earth life, adapted to the cold temperatures and exotic chemistry. Saturn has another intriguing moon called Enceladus. It's much smaller than Titan, only about 500 kilometers across, but it has geysers at its south pole that spray water ice and vapor into space. These geysers are visible from Earth-orbiting telescopes as plumes extending hundreds of kilometers above Enceladus's surface. The geysers come from a subsurface ocean beneath the south polar ice. Tidal heating from Saturn keeps this ocean liquid despite the cold temperatures. The geysers spray material from the ocean into space, where it freezes and falls back to the surface as snow or escapes entirely and becomes part of Saturn's E-ring, a faint ring made of ice particles from Enceladus's geysers. Spacecraft flying through Enceladus's plumes have detected water vapor, ice particles, salt, and organic molecules. The presence of salt indicates the subsurface ocean is in contact with a rocky seafloor, where chemical reactions between water and rock might provide energy for life. Enceladus is yet another potential habitat for life in our solar system. These discoveries have changed our understanding of where life might exist. We used to think life required a planet in the habitable zone around a star, the region where temperatures allow liquid water on the surface. But now we know moons can have liquid water oceans beneath their surfaces, heated by tidal forces rather than sunlight. This greatly expands the number of potential habitats for life in the universe. Many stars have planets, probably most stars. Astronomers have discovered thousands of exoplanets, planets orbiting other stars, and the discoveries continue accelerating as detection techniques improve. These exoplanets show tremendous diversity. There are hot Jupiters, gas giant planets orbiting very close to their stars, completing an orbit in just a few days. There are super-Earths, rocky planets larger than Earth but smaller than Neptune. There are planets in the habitable zones of their stars, where temperatures might allow liquid water. The discovery of exoplanets has confirmed that planet formation is a common process throughout the galaxy. Whenever a star forms, planets likely form around it. This means there are probably hundreds of billions of planetary systems in our galaxy alone, and trillions upon trillions in the observable universe. Most of these planetary systems are too distant for us to study in detail. The nearest known exoplanet is Proxima Centauri b, orbiting our nearest stellar neighbor at a distance of 4.2 light-years. We know this planet exists because we can detect the tiny gravitational wobble it causes in its star's motion, and we can measure the slight dimming of starlight when the planet passes in front of the star. But we can't see the planet directly or learn much about its surface conditions. For more distant exoplanets, we know even less. We can measure their mass, orbital period, and sometimes their radius, allowing us to calculate their density and make educated guesses about their composition. But we can't yet study their atmospheres in detail or determine if they have moons or rings or other features. This will change as technology improves. New telescopes designed specifically to study exoplanets will be able to analyze the atmospheres of nearby Earth-like planets, looking for gases that might indicate life, such as oxygen, methane, or other biosignatures. Within the next few decades, we might detect signs of life on planets orbiting other stars, confirming that life exists elsewhere in the universe. Or we might not. We might find that Earth-like planets are common but lifeless. We don't know yet. The question of whether life exists elsewhere is one of the great unanswered questions in science. We know life arose on Earth. We don't know if it arose elsewhere. The answer will come from observation, from studying other worlds, from patient searching and analysis. Returning to our own solar system, let's consider the smaller bodies. Asteroids, comets, and the various populations of objects that exist between and beyond the planets. These objects are leftovers from planet formation, material that never accumulated into planets, preserved in cold storage for billions of years. The asteroid belt between Mars and Jupiter contains millions of rocky objects ranging from grain-sized dust to Ceres, the largest asteroid at about 940 kilometers in diameter. These asteroids orbit the Sun in the same direction as the planets, most of them in slightly elliptical orbits that keep them between about 2.2 and 3.3 times Earth's distance from the Sun. The asteroid belt contains less total mass than Earth's moon. This seems surprising given how many asteroids there are, but most asteroids are very small. The four largest asteroids, Ceres, Vesta, Pallas, and Hygeia, contain about half the belt's total mass. The rest is distributed among millions of smaller objects, most of them just a few kilometers or less in diameter. Despite movies depicting asteroid belts as crowded, dangerous regions, the asteroid belt is mostly empty space. The average distance between asteroids is measured in millions of kilometers. Spacecraft have passed through the asteroid belt multiple times without needing to dodge asteroids. The belt is sparse, with asteroids widely separated, each one orbiting peacefully in its own path around the Sun. Asteroids occasionally collide, but such collisions are rare events, happening perhaps once every few million years for any given asteroid. When collisions do occur, they can shatter asteroids into fragments, creating families of asteroids with similar compositions and orbits. These collision fragments continue orbiting, some eventually falling into the Sun, others being ejected from the solar system, most remaining in the asteroid belt indefinitely. Some asteroids have orbits that cross Earth's orbit. These are called near-Earth asteroids, and they're of interest because they could potentially collide with Earth. Astronomers survey the sky continuously, cataloging near-Earth asteroids, calculating their orbits, predicting where they'll be in the future. So far, no large asteroid is known to be on a collision course with Earth for at least the next 100 years. Small asteroids hit Earth regularly, entering the atmosphere as meteors. Most burn up completely, creating bright streaks across the sky. Larger fragments sometimes survive to reach the ground as meteorites. These meteorites are pieces of asteroids, samples from the early solar system, valuable for scientific study. Meteorites show us what asteroids are made of. Some are stony, made of silicate minerals similar to rocks on Earth. Some are metallic, made mostly of iron and nickel. Some are a mixture of both. These compositions reflect different formation conditions in the early solar system and different histories of heating and cooling. The most primitive meteorites are called carbonaceous chondrites. They contain water, organic compounds, and minerals that have never been heated or altered since the solar system formed. They represent the original building blocks of planets, preserved unchanged for 4.6 billion years. Studying them is like studying samples from the protoplanetary disk, giving us direct information about the conditions and materials present when the solar system was forming. Beyond Neptune lies another region of small bodies called the Kuiper belt. This belt extends from about 30 to 50 times Earth's distance from the Sun and contains thousands of icy objects, similar to comets but larger and in more stable orbits. Pluto is the best-known Kuiper belt object, though it's no longer classified as a planet. Pluto is about 2,377 kilometers in diameter, smaller than Earth's moon. It has 5 known moons, the largest being Charon, about half Pluto's diameter. Pluto and Charon are so close in size that they're sometimes considered a binary system, two objects orbiting their common center of mass rather than a planet and moon. Pluto's orbit is quite elliptical and tilted relative to the main planet's orbits. It takes 248 Earth years to complete one orbit around the Sun. For part of its orbit, Pluto is actually closer to the Sun than Neptune, though the two never collide because their orbits are inclined to each other and the timing of their orbits prevents close approaches. The Kuiper Belt contains many objects similar to Pluto. Some are nearly as large, and one, Eris, is slightly more massive than Pluto. These objects are made mostly of ice and rock, remnants from the outer regions of the protoplanetary disk. They orbit peacefully, cold and dark, barely warmed by the distant Sun. Occasionally, gravitational perturbations send a Kuiper Belt object into the inner solar system. As it approaches the Sun, solar heating vaporizes some of its ice, creating a glowing atmosphere and tail. This is a comet. Comets are simply Kuiper Belt objects or similar icy bodies that have been perturbed into orbits that bring them close to the Sun. Short-period comets, those with orbital periods less than 200 years, come mostly from the Kuiper Belt. Long-period comets with orbital periods of thousands or millions of years come from an even more distant region called the Oort cloud. The Oort cloud is a spherical shell of icy objects surrounding the solar system at distances from about 2,000 to 100,000 times Earth's distance from the Sun. It's the most distant part of the solar system, extending nearly halfway to the nearest star. The Oort cloud contains trillions of objects, though they're so distant and faint that none have been directly observed. We know the Oort cloud exists because long-period comets come from all directions equally, suggesting they originate from a spherical distribution rather than a flat disk. These comets have orbital periods measured in thousands or millions of years. When they enter the inner solar system, many are on their first ever close approach to the Sun, arriving from the depths of interstellar space on highly elongated orbits. Some long-period comets pass through the inner solar system once and then return to the Oort cloud, not to return for millions of years. Others have their orbits changed by gravitational interactions with planets and become short-period comets, returning to the inner solar system every few years or decades. And some are ejected from the solar system entirely, sent into interstellar space to wander the galaxy forever. The Oort cloud represents the final frontier of the solar system, the gradual transition from the Sun's gravitational dominance to interstellar space. Objects in the outer Oort cloud are barely bound to the Sun. A passing star could easily perturb them into different orbits or capture them entirely. Over billions of years, the Oort cloud slowly loses objects to such perturbations, gradually diminishing, though it still contains an enormous number of objects. All these components, the planets, moons, asteroids, Kuiper Belt objects, Oort cloud comets, formed together 4.6 billion years ago from the same protoplanetary disk. They represent different outcomes of the planet formation process, shaped by their distance from the Sun, the materials available, and random chance. Together, they make up the solar system, our cosmic home, the small region of space dominated by our Sun's gravity. The solar system is stable on timescales of billions of years. The planets won't collide or be ejected. The Sun will continue shining steadily. The structure we see today will persist essentially unchanged for the Sun's remaining lifetime, about 5 billion years. This stability is comforting. Our cosmic environment is predictable and reliable, following the same patterns it has followed since its formation. Let's rest here for a moment with this knowledge. Planets form quietly through accumulation of dust and ice. They grow slowly over millions of years. They settle into stable orbits that persist for billions of years. Moons form around planets. Rings form and fade. Small bodies populate the spaces between planets. All of it follows natural laws. All of it is predictable. All of it unfolds at a patient pace. The universe creates worlds wherever stars form. Planets are abundant. Moons are common. The diversity of worlds is vast. Each planetary system is unique, yet all follow the same basic processes. Gravity gathers material. Temperature determines what condenses. Accretion builds larger objects from smaller ones. Time allows everything to settle into stable configurations. You live on one such world, formed billions of years ago, orbiting an ordinary star, part of a planetary system similar to countless others throughout the galaxy. Your world is special to you, but it's also one example among many. One planet among billions or trillions, formed through the same processes that create worlds everywhere. Rest in this knowledge. The formation of worlds is a quiet, patient process. Planets form whether anyone observes them or not. They orbit whether anyone inhabits them or not. The universe creates worlds continuously, has been doing so since the first stars formed, will continue doing so for trillions of years to come. You exist on one of these worlds, in one moment of its long history, able to observe and understand the processes that created it. That's remarkable. That's beautiful. And it is also peaceful, knowing that world formation is a natural, reliable process, happening throughout the universe, creating diverse and interesting places, following comprehensible laws. Let that knowledge settle gently into your mind as we continue exploring the quiet ways the universe creates structure and complexity. The process of world formation extends beyond the planets themselves to include the countless smaller features that make each world unique. Planetary surfaces are shaped by many processes, each operating at its own timescale, each following physical laws, each contributing to the final appearance we observe today. Impact craters are among the most common features on solid planetary surfaces. When an asteroid or comet strikes a planet or moon, the impact releases enormous energy, excavating a circular crater and throwing debris outward in all directions. The crater remains visible for billions of years unless other processes erase it. The moon's surface is covered with impact craters because the moon has no atmosphere to erode them and no geological activity to erase them through volcanism or tectonics. The craters simply accumulate over time, layer upon layer, creating a record of impacts stretching back billions of years. The oldest regions of the moon's surface are heavily cratered, saturated with overlapping craters of all sizes. Younger regions have fewer craters, having formed more recently through volcanic activity that covered older cratered terrain. By counting craters on different surfaces, planetary scientists can estimate the age of those surfaces. More craters mean an older surface, one that has been exposed to impacts for a longer time. Fewer craters mean a younger surface. This technique works throughout the solar system, allowing scientists to map out the geological history of planets and moons, even without bringing back rock samples for dating. Mercury's surface looks similar to the moon's, heavily cratered, ancient, unchanged for billions of years. Mercury has no atmosphere and no geological activity, so craters remain preserved indefinitely. The largest feature on Mercury is the Caloris Basin, an impact crater about 1,550 kilometers in diameter, created by a massive impact early in Mercury's history. Mars has impact craters too, but many have been partially eroded by wind and occasional water flows. Mars has a thin atmosphere, just 1% the density of Earth's. But over millions of years, even this thin atmosphere can erode surface features through wind-driven dust. Some Martian craters are pristine, sharp-edged, clearly recent. Others are degraded, their rims worn down, their interiors filled with dust. ancient features slowly being erased by erosion. Earth has far fewer visible craters than the Moon or Mars because Earth's surface is constantly being renewed. Plate tectonics recycles Earth's crust, erasing old craters by subduction or covering them with new rock. Erosion from water and wind wears away craters. Vegetation covers them. Only the youngest or largest craters remain visible. Earth's oldest known crater, Yarrabuba in Australia, is about 2.2 billion years old, ancient by human standards, but less than half Earth's age. The impact rate throughout the solar system has decreased dramatically since the early days. During the first billion years after the solar system formed, impacts were far more frequent as leftover planetesimals continue colliding with planets. This period is called the Late Heavy Bombardment, and it shaped the surfaces of all the rocky planets and moons. After this period ended, the impact rate dropped to much lower levels as most of the leftover debris was cleared away. The current impact rate is low, but not zero. Small asteroids continue to strike Earth regularly, usually burning up in the atmosphere as meteors. Larger impacts are rare, but inevitable given enough time. An asteroid large enough to create a significant crater strikes Earth perhaps once every few thousand to few million years, depending on the size threshold. The impact that killed the dinosaurs 66 million years ago was from an asteroid about 10 kilometers in diameter. It struck near what is now the Yucatan Peninsula in Mexico, creating the Chicxulub crater about 180 kilometers in diameter. The impact released energy equivalent to billions of nuclear weapons, creating a global catastrophe that caused a mass extinction, eliminating about 3/4 of all species on Earth, including all non-avian dinosaurs. But such large impacts are extremely rare. Nothing of that magnitude has struck Earth in the 66 million years since. Smaller impacts occur more frequently but cause only local damage. The Tunguska event in 1908, when an asteroid or comet fragment exploded in the atmosphere over Siberia, flattened trees over 2,000 square kilometers but caused no human casualties because the region was uninhabited. Planetary surfaces are also shaped by volcanism. Volcanic activity occurs when molten rock from a planet's interior rises to the surface and erupts. This can happen through various mechanisms, but all require internal heat to keep rock molten and pressure to drive it upward. Earth's volcanism is driven primarily by plate tectonics. Where tectonic plates collide, one plate can be forced under another in a process called subduction. The subducted plate descends into Earth's mantle, where high temperatures and pressures cause rock to melt, creating magma that rises and erupts at the surface, creating volcanic chains like the Andes Mountains or the island arcs of the Pacific. Where tectonic plates pull apart, magma rises to fill the gap, creating new oceanic crust. This happens along mid-ocean ridges, vast underwater mountain ranges where new seafloor is constantly being created. Most of this volcanism is invisible to us, happening deep underwater, but it's far more voluminous than all the volcanism on land combined. Earth's tectonic plates move slowly, just a few centimeters per year, about the rate your fingernails grow. But over millions of years, this adds up to thousands of kilometers of motion. Continents drift across Earth's surface, colliding and separating in a slow dance that has been ongoing for billions of years. The continents were arranged very differently in the past and will be arranged differently in the future. About 300 million years ago, all of Earth's continents were joined together in a supercontinent called Pangaea. Pangaea later broke apart, with the fragments drifting to their current positions. In the future, the continents will continue moving and might eventually collide again to form a new supercontinent. This cycle of supercontinent formation and breakup repeats every few hundred million years. driven by the continuous motion of tectonic plates. Mars once had volcanic activity, though it has long since ceased. Mars has the largest volcano in the solar system, Olympus Mons, a shield volcano about 600 kilometers in diameter and 25 kilometers high. For comparison, Mount Everest is about 8.8 kilometers above sea level. Olympus Mons is nearly 3 times taller and covers an area about the size of Arizona. Olympus Mons formed over hundreds of millions of years through countless eruptions, each one adding a thin layer of lava to the growing structure. The volcano is so large because Mars lacks plate tectonics. On Earth, a volcanic hotspot creates a chain of volcanoes as the tectonic plate moves over it, like the Hawaiian Islands. On Mars, with no plate motion, a hotspot creates a single enormous volcano, building up layer upon layer in the same location for hundreds of millions of years. Olympus Mons and the other Martian volcanoes are now extinct. Mars's interior has cooled to the point where widespread volcanism no longer occurs. The planet is geologically dead, or nearly so. Some evidence suggests occasional small eruptions might still occur, but nothing like the massive volcanism that created Olympus Mons. Venus has extensive volcanism, with hundreds of thousands of volcanic features covering its surface. Venus's surface is relatively young, only about 300 to 500 million years old, suggesting the entire surface was resurfaced by massive volcanic activity relatively recently in geological terms. We don't know if Venus still has active volcanism today, but some observations suggest it might. Venus's volcanism is not driven by plate tectonics. Venus appears to lack tectonic plates, or at least lacks the kind of plate tectonics Earth has. Instead, Venus might undergo periodic episodes of massive volcanism, when the entire surface is resurfaced over a relatively short period, geologically speaking, followed by long periods of quiescence. This is speculative, though, as Venus's thick atmosphere makes surface observations difficult. Jupiter's innermost Galilean moon has the most intense volcanism in the solar system. Hundreds of active volcanoes cover Io's surface, constantly erupting, creating enormous lava flows and volcanic plumes that reach hundreds of kilometers into space. This volcanism is driven entirely by tidal heating from Jupiter, as discussed earlier. Io's volcanic eruptions are so frequent that they completely resurface the moon every few thousand years. No impact craters are visible on Io because they're buried by lava flows before they can accumulate. Io is a world of continuous volcanic activity, constantly changing, constantly renewing itself through eruptions driven by the relentless tidal forces from Jupiter. Europa's icy surface shows evidence of cryovolcanism, where liquid water or slushy ice erupts onto the surface instead of molten rock. Europa's surface has relatively few impact craters, suggesting it's young, constantly being renewed. The ice appears to be breaking apart, shifting, and new ice is forming in the gaps, driven by the subsurface ocean moving beneath the ice shell. Enceladus's geysers at its south pole are a form of cryovolcanism, spraying water, ice, and vapor from the subsurface ocean into space. These geysers operate continuously, though their intensity varies. They represent active geological processes happening right now on a small, icy moon orbiting Saturn. Planetary surfaces are also shaped by erosion, the gradual wearing away of rock and soil by various processes. On Earth, water is the dominant erosion agent, carving valleys, creating river systems, shaping coastlines. Wind also erodes surfaces, particularly in dry regions, creating sand dunes, wearing away rock formations, transporting dust across continents. Mars has erosion too, despite its thin atmosphere and lack of liquid water today. Ancient river valleys carved into the Martian surface show that water once flowed freely on Mars. billions of years ago when Mars had a thicker atmosphere and warmer temperatures. These river valleys are now dry, preserved features from Mars's wetter past, slowly being filled in by wind-blown dust. Wind erosion continues on Mars today. Dust storms occur regularly, sometimes covering the entire planet. These storms transport dust from one region to another, gradually reshaping the surface. Sand dunes migrate slowly across the Martian landscape, driven by wind, moving a few meters per Earth year. Titan, Saturn's largest moon, has erosion from liquid methane. Methane rain falls from Titan's clouds, creating rivers that carve channels in Titan's icy surface. These channels flow into lakes and seas of liquid methane, creating landscapes remarkably similar to Earth's despite the extremely different conditions and materials involved. Venus has minimal erosion because its surface is so hot that rocks don't weather the way they do on Earth. The temperature on Venus is about 465 degrees Celsius, hot enough to melt lead. At these temperatures, rocks behave differently than on Earth, and the thick atmosphere, while capable of moving material through wind, doesn't cause the same kind of erosion we see on Earth or Mars. The diverse erosion processes throughout the solar system show how planetary surfaces respond to their environments. Where liquid exists, it carves channels and shapes landscapes. Where wind blows, it transports material and creates dunes. Where temperatures are extreme or atmospheres are absent, surfaces remain largely unchanged except by impacts and volcanism. Planetary interiors are just as important as surfaces in determining a world's characteristics. A planet's interior structure depends on its size, composition, and thermal history. All of these factors interact to create the conditions we observe. Earth has a layered interior structure. At the center is a solid iron core, about 1,220 kilometers in radius, surrounded by a liquid iron outer core, extending to about 3,480 kilometers from Earth's center. Above the outer core is the mantle, made of hot but solid rock, extending to about 35 kilometers below the surface on average. The outermost layer is the crust, the thin rocky shell we live on, ranging from about 5 kilometers thick under oceans to about 70 kilometers thick under major mountain ranges. This layered structure formed through differentiation, a process where denser materials sink toward the center and lighter materials rise toward the surface. Early in Earth's history, when the planet was molten or partially molten from the heat of formation and radioactive decay, iron and nickel sank toward the center, forming the core. Lighter silicate rocks rose toward the surface, forming the mantle and crust. The liquid outer core is responsible for Earth's magnetic field. As Earth rotates, the liquid iron in the outer core flows in complex patterns, generating electric currents. These electric currents create a magnetic field that extends far into space, forming the magnetosphere. This magnetic field protects Earth's atmosphere from being stripped away by the solar wind, a stream of charged particles constantly flowing from the sun. Mars once had a strong magnetic field, evidenced by magnetized rocks in Mars's ancient crust. But Mars's magnetic field shut down billions of years ago when Mars's core cooled enough that it no longer generated a dynamo. Without a magnetic field, Mars's atmosphere was gradually stripped away by the solar wind, transforming Mars from a world with liquid water and a thick atmosphere into the cold, dry planet we see today. Venus has no magnetic field, despite being similar in size to Earth. We don't know exactly why. Venus rotates very slowly, which might prevent the generation of a magnetic field, even if its core is still liquid. Or Venus's core might be entirely solid, no longer capable of generating a dynamo. Mercury has a weak magnetic field, surprising for such a small planet. Mercury's core is unusually large relative to its total size, making up about 85% of the planet's radius. This large core might still be partially liquid, generating a weak magnetic field through dynamo action despite Mercury's slow rotation. The gas giants all have strong magnetic fields generated by dynamos in their interiors. These planets don't have liquid iron cores like Earth, but they have metallic hydrogen in their deep interiors. Hydrogen becomes metallic under extreme pressure, able to conduct electricity. Convection and rotation in the metallic hydrogen layers generate powerful magnetic fields. Jupiter's magnetic field is the strongest in the solar system, about 20,000 times stronger than Earth's. This field extends millions of kilometers into space, trapping charged particles and creating intense radiation belts around Jupiter. These radiation belts are hazardous to spacecraft, requiring special shielding for instruments and electronics. Saturn's magnetic field is also strong, though weaker than Jupiter's. The field is remarkably symmetric, aligned almost perfectly with Saturn's rotation axis. This symmetry is unusual and not fully understood. Uranus and Neptune have complex, tilted magnetic fields that don't align with their rotation axes. Uranus's magnetic field is tilted 59 degrees relative to its rotation axis, and Neptune's is tilted 47 degrees. These unusual configurations might result from the magnetic fields being generated in layers closer to the surface rather than deep in the interior, or from complex internal structures we don't fully understand. All of these magnetic fields interact with the solar wind, creating magnetospheres, regions of space where the planet's magnetic field dominates over the sun's magnetic field. Earth's magnetosphere extends about 10 Earth radii toward the sun and much farther in the opposite direction, creating a long tail blown back by the solar wind. Particles from the solar wind can enter the magnetosphere near the magnetic poles, following magnetic field lines down into the upper atmosphere. When these particles collide with atmospheric gases, they create auroras. The northern lights and southern lights on Earth, beautiful glowing displays of green, red, and purple light dancing across the polar skies. Jupiter, Saturn, Uranus, and Neptune all have auroras too, visible in ultraviolet light. Jupiter's auroras are particularly intense, driven by the planet's strong magnetic field and fast rotation. The auroras on these giant planets operate on the same basic principle as Earth's auroras, but on much larger scales and with much more energy. The heat inside planets comes from several sources. Some heat remains from the planet's formation, when gravitational potential energy was converted to heat as material fell together. Some heat comes from radioactive decay of elements like uranium, thorium, and potassium in the planet's interior. For giant planets, some heat comes from gravitational contraction as the planet slowly shrinks over time. Jupiter radiates about 1.7 times as much energy as it receives from the Sun, meaning it has a significant internal heat source. This heat comes mostly from slow gravitational contraction. As Jupiter slowly contracts, gravitational potential energy is converted to heat, which radiates into space. This process will continue for billions of years as Jupiter gradually cools and contracts. Saturn also radiates more energy than it receives from the Sun, about 1.8 times as much. In addition to gravitational contraction, Saturn might have another heat source from helium differentiation. Helium might be slowly separating from hydrogen in Saturn's interior and sinking toward the core, releasing gravitational energy as it does so. Uranus is unusual among the giant planets because it radiates very little excess heat, only about 1.06 times what it receives from the Sun. This suggests Uranus has less internal heat than the other giants, possibly because it lost heat through some event in its past, or because its interior has better thermal insulation, trapping heat inside rather than allowing it to escape. Neptune radiates about 2.6 times as much energy as it receives from the Sun, despite being farther from the Sun than Uranus and similar in size. This indicates Neptune has more internal heat than Uranus, though we don't know exactly why the two planets differ so much. The rocky planets also have internal heat, though much less than the giants. Earth's internal heat drives plate tectonics, volcanism, and the dynamo that creates the magnetic field. This heat is gradually escaping to space, slowly cooling the planet over billions of years. Eventually, Earth's interior will cool enough that plate tectonics stops. Volcanism ceases, and the magnetic field shuts down, though this won't happen for billions of years. Mars is already cooled to this point. Its volcanism has largely ceased. Its magnetic field shut down billions of years ago, and the planet is geologically dead or nearly so. Mars' smaller size meant it cooled faster than Earth, losing its internal heat more quickly because smaller objects have less volume relative to surface area, allowing heat to escape more efficiently. Venus might still be geologically active, possibly with ongoing volcanism and a hot interior, despite lacking plate tectonics. Venus's size is similar to Earth's, so it should cool at a similar rate. But Venus's different geological history has led to different surface processes. Mercury's large core is still partially molten, evidenced by its weak magnetic field, despite Mercury's small size. Mercury might have cooled more slowly than expected, or it might have an unusually high concentration of radioactive elements providing extra heat. The Moon's interior is mostly solid and cool. Seismometers left on the Moon by Apollo astronauts detected moonquakes, showing the Moon still has some internal activity, but it's minimal compared to Earth. The Moon is essentially a cold, dead world geologically, with no volcanism, no magnetic field, and minimal internal heat. All these internal processes, these invisible workings beneath planetary surfaces, shape the worlds we observe. They determine whether a planet has a magnetic field, whether it has volcanism, whether its surface is geologically active or ancient and unchanging. They operate slowly, over millions and billions of years, following the laws of thermodynamics, gradually releasing heat accumulated during formation or generated by radioactive decay. Planetary atmospheres add another layer of complexity to world formation and evolution. Atmospheres form through several processes. Some atmospheric gases were present in the original material that formed the planet. Some came from volcanic outgassing as the planet's interior released volatile compounds. Some came from comet impacts delivering water and other volatiles. Some came from chemical reactions on the surface. Earth's atmosphere has evolved dramatically over its history. The early atmosphere, about 4 billion years ago, contained very little oxygen. It was mostly nitrogen and carbon dioxide, with significant amounts of water vapor, methane, and ammonia. This atmosphere came from volcanic outgassing and comet impacts. About 4 billion years ago, oxygen began accumulating in Earth's atmosphere, produced by photosynthetic bacteria in the oceans. This was a gradual process taking hundreds of millions of years. Eventually, oxygen levels rose high enough to create an ozone layer in the upper atmosphere, which shields the surface from harmful ultraviolet radiation from the sun. The current atmosphere is about 78% nitrogen, 21% oxygen, and 1% argon, with trace amounts of carbon dioxide, water vapor, and other gases. This composition has remained relatively stable for hundreds of millions of years, though carbon dioxide levels have varied significantly depending on volcanic activity, weathering rates, and biological processes. Mars once had a much thicker atmosphere than it does now. Evidence suggests Mars's early atmosphere might have been thick enough to keep water liquid on the surface. But without a magnetic field to protect it, The solar wind gradually stripped away Mars's atmosphere over billions of years. The atmosphere became thinner, temperatures dropped, and water froze or escaped into space. Venus's atmosphere is extremely thick, with surface pressure about 92 times Earth's sea level pressure. The atmosphere is 96% carbon dioxide, creating a powerful greenhouse effect that keeps surface temperatures at 465 degrees Celsius. Venus might have had liquid water early in its history, but as the sun grew brighter over time, rising temperatures caused the water to evaporate. Water vapor is a greenhouse gas, trapping more heat, causing more evaporation, creating a runaway greenhouse effect that boiled away Venus's oceans and left a hot, dry planet we see today. Titan has a thick nitrogen atmosphere similar to Earth's, though much colder. The atmosphere is about 95% nitrogen and 5% methane, with surface pressure 1.5 times Earth's. The methane plays a role similar to water on Earth, existing as gas, liquid, and solid depending on temperature and pressure, creating a methane cycle with rain, rivers, and lakes. The giant planets' atmospheres are essentially the planets themselves. There's no clear boundary between atmosphere and interior. The atmosphere gradually becomes denser and hotter with depth, transitioning smoothly from gas to liquid to possibly solid at the very center. These atmospheres are mostly hydrogen and helium, with small amounts of methane, ammonia, water vapor, and other compounds. Jupiter's atmosphere has colorful bands and zones created by atmospheric circulation. Rising warm gas creates light-colored zones. Sinking cool gas creates dark-colored belts. The colors come from different chemical compounds that condense at different altitudes and temperatures. The bands remain remarkably stable over time, though individual features like storms come and go. The Great Red Spot on Jupiter is a giant storm that has persisted for at least 350 years, since it was first observed telescopically. The storm is slowly shrinking, for reasons we don't fully understand, but it remains one of the largest storms in the solar system, large enough to swallow Earth completely. Saturn's atmosphere has similar banding, but less pronounced colors. Saturn appears more uniform than Jupiter, with a pale yellow color from ammonia crystals in the upper atmosphere. But Saturn occasionally develops large storms, including spectacular white spots that appear every few decades in Saturn's northern hemisphere. Uranus and Neptune appear relatively featureless in visible light because their atmospheres contain methane, which absorbs red light, giving these planets a blue or blue-green color. But observations at other wavelengths reveal banding and storm systems similar to Jupiter and Saturn, just less visible to the eye. Neptune has the fastest winds in the solar system, with wind speeds reaching up to 2,100 kilometers per hour. These winds drive storm systems around the planet, creating features similar to Jupiter's Great Red Spot, but less stable. Neptune's storms appear and disappear over years or decades, unlike Jupiter's centuries-long storms. All these atmospheric processes create weather patterns, temperature variations, cloud formations, and other phenomena that make each world unique. Atmospheres interact with surfaces, with incoming sunlight, with internal heat, with magnetic fields, creating complex systems that evolve over time. Some worlds have almost no atmosphere. Mercury's atmosphere is extremely tenuous, barely qualifying as an atmosphere at all. It consists of atoms knocked off the surface by solar wind and micrometeorite impacts. These atoms escape into space quickly, so the atmosphere must be constantly replenished. Earth's moon has no appreciable atmosphere, just an extremely tenuous layer of atoms similar to Mercury's. With no atmosphere, the moon's surface experiences extreme temperature variations, from about 127 degrees Celsius in sunlight to minus 173 degrees Celsius in shadow. Triton, Neptune's largest moon has a thin nitrogen atmosphere maintained by nitrogen ice sublimating from Triton's surface. The atmosphere is extremely thin, with surface pressure only about 14 microbars, roughly 70,000 times thinner than Earth's atmosphere, but it's thick enough to create thin nitrogen frost deposits and possibly support winds. The diversity of atmospheres throughout the solar system shows how many factors influence atmospheric evolution. Planetary mass determines whether a planet can hold an atmosphere gravitationally. Temperature determines which compounds remain gaseous versus condensing or freezing. Magnetic fields protect atmospheres from solar wind erosion. Geological activity replenishes atmospheres through outgassing. Biological activity can dramatically alter atmospheric composition, as happened on Earth. All of these processes operate simultaneously, interacting in complex ways, creating the unique conditions observed on each world. No two planets are exactly alike because each formed under slightly different conditions and evolved along its own path. As we rest and reflect on the formation and evolution of worlds, we can appreciate the patience required for these processes. Planets don't form overnight. They grow slowly over millions of years. Their surfaces are shaped gradually by impacts, volcanism, and erosion over billions of years. Their atmospheres evolve slowly as gases escape to space. New gases are added by volcanism or impacts, and chemical reactions alter composition. Everything happens on vast timescales that dwarf human experience. 1,000,000 years is a long time to us, but it's a brief moment in planetary evolution. 1,000,000,000 years seems almost infinite to human minds, but it's less than a quarter of the solar system's age. Planets operate on timescales that make human lifetimes and human civilizations seem instantaneous. Yet, despite these enormous timescales, the processes are comprehensible. We can understand how planets form. We can calculate how their interiors evolve. We can model atmospheric circulation and predict how atmospheres change over time. The timescales are vast, but the physics is knowable. This creates a profound sense of perspective. Your entire life, all of human history, all of recorded civilization, is just a tiny moment in the life of Earth. Earth itself is just one planet among billions. Its formation and evolution follow the same processes that create worlds everywhere throughout the universe. You live on a world that formed 4.6 billion years ago through patient accumulation of dust and rock. This world has been geologically active for its entire history, constantly renewing its surface, maintaining its magnetic field, hosting an atmosphere that has evolved dramatically over time. This world will continue existing for billions more years, long after humanity is gone, continuing to orbit the sun, continuing to follow the same physical laws that have governed it since its formation. Rest in this knowledge. The formation of worlds is a natural process, happening throughout the universe, creating diverse and interesting places. Each world has its own history, its own characteristics, its own evolution. And all of it follows comprehensible laws. All of it unfolds predictably. All of it creates the cosmic environment in which we exist. The silent formation of worlds continues everywhere, right now, around young stars in our galaxy and in galaxies across the universe. Planets are forming, growing from dust to pebbles to boulders to worlds. This has been happening for billions of years. It will continue for billions more. The universe creates worlds patiently, reliably, continuously, following the same patterns that created Earth, following the same laws that govern everything. Let this knowledge be peaceful. World formation requires no conscious guidance, no intervention, no purpose beyond the natural operation of physical law. Gravity gathers material. Temperature determines composition. Time allows accumulation. The result is planets, diverse and numerous, scattered throughout the cosmos. You exist on one such world, able to observe others, able to understand the processes that created them all. That understanding connects you to the broader universe, shows you that Earth is part of a larger pattern, demonstrates that the universe operates according to noble principles. Rest easy in this understanding. Worlds form quietly, patiently, following natural law. They evolve slowly over vast timescales. They create the stable environments necessary for complexity and possibly for life. And they do all of this without urgency, without drama, just through the steady operation of gravity, thermodynamics, and chemistry over millions and billions of years. The universe is patient in its creation of worlds. We can be patient in our observation and understanding of them. There's no rush. The processes have been occurring for billions of years. They'll continue for billions more. We can study them at our own pace, learning gradually, building understanding piece by piece, appreciating the beauty and complexity of planetary systems without feeling overwhelmed by their vastness or timescales. Let yourself relax into this perspective. Worlds form, worlds evolve. Worlds exist in vast numbers throughout the universe, and all of it happens according to comprehensible natural law. All of it creates beauty and diversity. All of it invites patient observation and thoughtful understanding. The quiet dance of cosmic time itself behaves differently across the universe, flowing at different rates depending on gravity and motion. This is not metaphor or poetry. It's literal fact, confirmed by countless experiments and observations. Time is flexible, malleable, influenced by the physical conditions around it. Understanding how time works throughout the cosmos reveals one of the universe's most profound and calming truths. There is no single universal now that everything shares. Let's begin gently with something familiar before moving to the strange. On Earth's surface, time passes at a rate we consider normal, the rate human civilization has always experienced. Clocks tick at their expected pace. Days last 24 hours. Years last 365.25 days. Everything proceeds in the familiar rhythm we've known throughout history. But even on Earth, time doesn't flow uniformly everywhere. At higher altitudes, farther from Earth's center, gravity is slightly weaker and time flows slightly faster. The difference is tiny. The clock on a mountaintop runs faster than a clock at sea level by only a few nanoseconds per day. But the difference is real and measurable. The Global Positioning System, GPS, must account for these time differences to work accurately. GPS satellites orbit about 20,000 kilometers above Earth's surface, where Earth's gravity is weaker than at the surface. Time flows faster for the satellites than for receivers on the ground. If GPS didn't correct for this time dilation, position calculations would drift by several kilometers per day, making the system useless. The correction is straightforward once you know the physics. Einstein's general theory of relativity predicts exactly how much faster time flows at different gravitational potentials. The satellite's clocks are adjusted to account for this, ensuring they remain synchronized with ground-based clocks despite experiencing time at a different rate. This demonstrates something remarkable. Time is not absolute. It's not the same everywhere. It depends on local conditions, specifically on the strength of gravity. The stronger the gravity, the slower time flows. The weaker the gravity, the faster time flows. This effect is called gravitational time dilation. Near a massive object, like a planet or star, time flows more slowly than far from such objects. The difference is usually tiny, unless the object is extremely massive or you're very close to it. But the effect is always present, always real, always measurable if you have precise enough clocks. Near a black hole, gravitational time dilation becomes extreme. A black hole is a region where matter has collapsed to such high density that its gravity is overwhelming. At the black hole's event horizon, the boundary beyond which nothing can escape, gravity is so strong that time, as measured by a distant observer, appears to stop completely. Imagine watching an object fall toward a black hole's event horizon. As the object approaches the horizon, it appears to move slower and slower. Light from the object becomes increasingly redshifted, stretched to longer and longer wavelengths by the intense gravity. The object appears to freeze just above the horizon, never quite crossing it, growing dimmer and redder until it fades from view. But this is only how it appears to a distant observer. From the falling object's perspective, nothing special happens at the event horizon. Time passes normally. The object crosses the horizon in finite time and continues falling toward the singularity at the black hole's center. There's no sensation of time slowing down, no awareness that distant observers see things differently. This difference in perspective is fundamental to understanding relativistic time. There is no single correct rate at which time flows. Different observers, in different gravitational fields or moving at different speeds, experience time at different rates. Each observer's experience is equally valid. Time is relative, not absolute. Motion also affects time's flow. This is called velocity-time dilation, another prediction of Einstein's relativity. An object moving at high speed experiences time more slowly than a stationary object. Again, the effect is tiny at everyday speeds, but becomes significant at speeds approaching the speed of light. If you could travel at 90% of the speed of light for 1 year by your clock, you would age 1 year. But to stationary observers watching you, more than 2 years would pass. If you return to your starting point, you would find that everyone else had aged more than twice as much as you. This is not an illusion or a clock malfunction. It's how time actually works at high speeds. This has been confirmed experimentally many times. Particles called muons, created when cosmic rays strike Earth's upper atmosphere, live for only about 2.2 microseconds when at rest. But when moving at nearly the speed of light, they live much longer from our perspective, allowing them to reach Earth's surface before decaying. From the muon's perspective, his lifetime is still 2.2 microseconds, but the distance to Earth's surface appears contracted due to another relativistic effect, so it still reaches the surface in its normal lifetime. These time effects are not science fiction. They're established physics, tested countless times, incorporated into technologies we use daily. Time really does flow at different rates in different circumstances. The universe doesn't share a single unified clock that advances everywhere simultaneously. Instead, time is local, personal, dependent on each observer's motion and gravitational environment. This might seem strange or unsettling at first, but it can also be deeply calming. It means the universe is even more spacious than we thought. Not just spatially vast, but temporally flexible. Different regions of space can exist at different rates of time. Events that appear simultaneous to one observer might not be simultaneous to another. The rigid framework of absolute time we imagine doesn't actually exist. Let's consider the implications at cosmic scales. Light from distant galaxies takes billions of years to reach us, as we discussed earlier. But whose years? From our perspective, the light travels for billions of our years. But light itself experiences no passage of time. Photons, traveling at the speed of light, experience no time passage at all. From a photon's perspective, if it could have one, its emission and absorption are instantaneous, happening at the same moment, even if billions of years pass for us between those events. This seems paradoxical, but it's perfectly consistent with relativity. Time dilation approaches infinity as speed approaches the speed of light. At the speed of light, time dilation is infinite. meaning no time passes for the light itself. The photon exists in a timeless state, connecting its emission to its absorption directly, without experiencing the intervening years. We cannot travel at the speed of light. Matter with mass cannot reach that speed, as it would require infinite energy. But we can imagine traveling very close to the speed of light. If you could travel at 99.99% of light speed toward a galaxy 100 million light years away, the journey would take only about 140,000 years by your clock. From Earth's perspective, it would take slightly over 100 million years. But you would experience the journey as lasting only 140,000 years. A long time, but far shorter than 100 million years. This raises fascinating questions about interstellar travel. The vast distances between stars seem insurmountable if you consider them in terms of Earth time. But if you could travel fast enough, time dilation would compress the journey from your perspective. You could, in principle, travel to distant galaxies within a human lifetime by your clock, even though millions or billions of years would pass on Earth while you traveled. This is not currently possible with any foreseeable technology. Accelerating to such speeds would require enormous energy, and protecting against collisions with interstellar gas and dust would be extremely challenging at such velocities. But it's not forbidden by physics. It's merely impractical with current technology. The flexibility of time also affects our understanding of cosmic history. When we look at distant galaxies, we see them as they were billions of years ago. But we need to be careful about what we mean by ago. From our perspective, observing from Earth in 2026, we see those galaxies as they were billions of years in the past, by Earth time. But the galaxies themselves have experienced those billions of years in their own reference frames, aging and evolving according to their own clocks. There's no universal now extending across the universe. When we say the universe is currently 13.8 billion years old, we mean from the perspective of observers moving with the cosmic expansion, the average motion of galaxies. Different observers, moving differently or in different gravitational fields, would calculate slightly different ages. These differences are usually tiny for practical purposes, but they're conceptually important. They remind us that time is not a rigid framework imposed on the universe from outside. Time is part of the universe, woven into its fabric, flexible and dynamic, responding to matter and energy. The expansion of the universe itself affects time in interesting ways. As the universe expands, distances between galaxies increase. Light traveling between galaxies gets stretched to longer wavelengths, a phenomenon called cosmological redshift. This redshift is often described as a Doppler shift, similar to how the pitch of a siren changes as it moves. But it's more accurate to think of it as light being stretched by the expansion of space itself. This stretching affects time measurements. When we observe a distant galaxy, we see all its processes happening in slow motion. A supernova that takes a few weeks to brighten and fade, measured in the galaxy's own reference frame, appears to take longer when we observe it from Earth. The more distant the galaxy, the more pronounced this time dilation effect. This is actually observed in distant supernova. Type AZ supernovas at high redshift take longer to brighten and fade than nearby Type Ia supernovas, exactly as predicted by cosmological time dilation. This effect is independent of the light travel time. It's not about how long the light takes to reach us, but about how time itself flows differently in the expanding universe. All of this demonstrates that the universe operates on its own schedule, indifferent to our human sense of time. Billions of years pass easily. Time flows at different rates in different places. The universe expands, carrying galaxies apart, stretching light and time itself in the process. And all of it unfolds according to physical law, predictable and comprehensible. Let's think about time on even larger scales. The universe is 13.8 billion years old now. But what about the future? The universe will continue expanding for trillions upon trillions of years, possibly forever. Different eras of the universe have different characteristics. And we happen to exist in a particular era called the stelliferous era, the age of stars. The stelliferous era began a few hundred million years after the Big Bang, when the first stars formed, and it will continue for many trillions of years into the future, as long as there's hydrogen gas to form new stars. We're currently about 13.8 billion years into this era, still relatively early considering it will last for trillions of years. Eventually, the galaxy will run out of hydrogen gas. Star formation will cease. The last stars will burn out. The smallest, coolest red dwarf stars will be the last to die, shining for tens of trillions of years before finally exhausting their fuel and fading to cold darkness. After the last stars die, the universe will enter what's called the degenerate era, dominated by stellar remnants. White dwarfs, neutron stars, black holes. These objects don't shine like stars. They emit only faint thermal radiation, gradually cooling toward absolute zero. The universe will be dark, cold, almost unchanging, with only occasional events like stellar collisions breaking the monotony. The degenerate era will last unimaginably long, perhaps 1,037 years or more. During this time, very little happens. The stellar remnants slowly cool. Galaxies continue their stately orbits, though galaxy collisions become rare as the expansion of the universe carries galaxy clusters apart. Time continues, but the universe becomes increasingly quiet, increasingly dark, increasingly cold. Eventually, even the stellar remnants might decay. Protons, the particles that make up atomic nuclei, might not be stable over extremely long timescales. Some theories predict protons decay with a half-life of perhaps 1,034 years or longer. If true, then over timescales of 1,040 years or more, all matter would gradually decay into lighter particles and radiation. White dwarfs, neutron stars, even planets would slowly evaporate as their constituent protons decay. After proton decay, if it occurs, the universe would enter the black hole era. Black holes would be the only massive objects remaining, slowly evaporating through a process called Hawking radiation. Stephen Hawking showed that black holes emit thermal radiation due to quantum effects near their event horizons. This radiation is extremely faint, much colder than the cosmic microwave background for large black holes. But over long enough timescales, it causes black holes to evaporate completely. A solar mass black hole would take about 1,067 years to evaporate. A supermassive black hole containing billions of solar masses would take about 10,100 years. These timescales are so vast they defy comprehension. They make the current age of the universe, 13.8 billion years, seem like an instant in comparison. After the last black hole evaporates, the universe would enter what's called the dark era, containing only diffuse radiation and fundamental particles scattered across ever-expanding space. The universe would be cold, approaching absolute zero temperature, dark, with no structures larger than individual particles. No sources of light, no change except the continuing expansion of space itself. This might seem bleak, but it's simply the logical conclusion of the universe's evolution under the laws of physics as we understand them. The universe began in a hot, dense state. It expanded and cooled. Structures formed: galaxies, stars, planets. These structures are temporary, lasting billions or trillions of years, but eventually they dissipate. The universe tends toward increasing entropy, toward disorder, toward uniformity, and coldness. This is the second law of thermodynamics operating on cosmic scales. Entropy always increases in a closed system. The universe as a whole is a closed system. There's nothing outside it exchanging energy with it. So entropy increases, order decreases, and the universe slowly runs down toward a state of maximum entropy and minimum organization. But this takes unimaginably long. The current universe, full of stars and galaxies, will persist for trillions of years. Even after stars die, stellar remnants will exist for vastly longer. The universe has plenty of time remaining before reaching anything like a final state. And we don't know everything. Our understanding of physics might be incomplete. There might be processes we haven't discovered that could change the universe's ultimate fate. Dark energy, the mysterious component driving the universe's accelerating expansion, might behave differently in the future than it does now. The laws of physics themselves might change over sufficiently long timescales. These are speculative possibilities, not predictions, but they remind us that our knowledge is limited. We understand the universe well enough to make predictions billions or trillions of years into the future with reasonable confidence. But predictions extending to 10,100 years or beyond are necessarily uncertain, based on extrapolating known physics far beyond the regime where we've tested it. What we can say with confidence is that the universe operates on timescales vastly exceeding human comprehension. A human lifetime is about 109 seconds, roughly 1 billion seconds. The current age of the universe is about y seconds. The time until the last star's burnout is perhaps 1,021 seconds. The time until the last black holes evaporate is perhaps 10,107 seconds or more. These numbers are so large they lose meaning. Our brains didn't evolve to grasp such timescales. We can write them down, calculate with them, reason about them abstractly, but we can't truly visualize or emotionally comprehend them the way we comprehend a year or a lifetime. And yet, the universe proceeds through these timescales effortlessly, indifferently. Time continues whether we comprehend it or not. The universe doesn't hurry. It doesn't wait. It simply exists, evolving according to physical law, unfolding across timescales that make civilizations and species seem ephemeral. This perspective can be humbling, but it can also be peaceful. Nothing is permanent in the universe. Stars are temporary. Galaxies are temporary. Even atoms might be temporary over long enough timescales. Everything changes. Everything evolves. Everything eventually ends. But the changes happen slowly, over vast periods, giving ample time for complexity and beauty to emerge and persist. You exist in a particular moment of cosmic time. The universe is currently 13.8 billion years old, still in its stelliferous era, still full of shining stars, still forming new stars and gas clouds throughout galaxies. This is a golden age of the universe in some sense, an era of activity and light, before the slow decline toward darkness and cold begins in earnest. Your moment of existence coincides with a time when the universe is interesting, when stars shine, when planets orbit, when complexity exists. You live on a planet orbiting a stable star, in a galaxy containing hundreds of billions of similar stars, in a universe containing hundreds of billions of similar galaxies. All of this exists right now, in this era, available to observe and study and appreciate. Billions of years in the future, this won't be true. Stars will have burned out. Galaxies will have dispersed. The universe will be darker, quieter, colder. But that's far in the future, measured in timescales that dwarf all of human history. For now, the universe shines. Stars create light and warmth. Planets orbit peacefully. Time flows at its varying rates throughout space, flexible and strange, but predictable. And conscious observers like you can exist briefly in the midst of this vast cosmic unfolding, able to observe and understand small pieces of it. Let's return to thinking about time in ways more directly relevant to our experience. The Earth orbits the Sun once per year, defining our year. The Earth rotates once per day, defining our day. The Moon orbits Earth once per month, roughly defining our month. These cycles have repeated billions of times since the solar system formed. The Earth's orbit is very stable. It doesn't change significantly from year to year. The orbital period is 365.25 days, hence the need for leap years to keep our calendar synchronized with the seasons. This orbital period has remained essentially constant for billions of years. The Earth's rotation, however, is gradually slowing down. Tidal forces from the Moon transfer angular momentum from Earth's rotation to the Moon's orbit, slowing Earth's rotation and causing the Moon to gradually recede from Earth. This process is extremely slow. Earth's day lengthens by about 1.7 milliseconds per century. Over billions of years, this adds up to significant changes. When the Earth first formed, about 4.6 billion years ago, a day was only about 6 hours long. The Moon was much closer, perhaps only 20,000 kilometers away, instead of the current 384,000 kilometers. Over billions of years, tidal forces slowed Earth's rotation and pushed the Moon farther away, creating the 24-hour day and current Moon distance we observe today. This process will continue into the future. Eventually, in about 50 billion years, if the process continues uninterrupted, Earth's rotation will slow to the point where one side always faces the Moon, just as the Moon currently keeps one side always facing Earth. At that point, Earth's day would equal the lunar month, both about 47 current days long. The Moon would appear stationary in the sky, always in the same position, visible from one hemisphere, but never from the other. But this won't actually happen, because the Sun will evolve into a red giant in about 5 billion years, long before Earth becomes tidally locked to the Moon. The Sun's expansion might engulf Earth entirely, or at least render it uninhabitable. The tidal locking process will be interrupted by the Sun's evolution. These far future predictions are interesting, but don't affect our current experience. For now, and for millions of years to come, Earth will continue its familiar cycles. Days will last 24 hours, give or take tiny amounts. Years will last 365.25 days. The seasons will continue their regular pattern. The sun will rise and set predictably. This predictability is comforting. Despite the strangeness of relativistic time and the vast cosmic timescales we've discussed, our immediate experience of time is stable and reliable. Days follow nights. Seasons follow each other in order. Years accumulate steadily. We can plan, anticipate, remember, all based on the reliable flow of time we experience. Time, despite its flexibility at cosmic scales, feels constant and steady in our daily lives. And for practical purposes, it is. The relativistic effects that make time flexible are too small to notice in everyday life. GPS corrections aside, we can treat time as absolute, universal, flowing at the same rate everywhere, without error. This dual nature of time, strange and flexible at cosmic scales, but familiar and steady in daily life, reflects a general pattern in physics. The universe operates according to laws that seem counterintuitive when pushed to extremes but reduced to familiar, classical behavior under everyday conditions. Quantum mechanics governs the behavior of atoms and subatomic particles with probability and uncertainty. But large objects made of many atoms behave classically, deterministically, as we expect from everyday experience. Relativity makes time and space flexible at high speeds and strong gravity. But at low speeds and weak gravity, Time and space behave as Newton described them centuries ago. The universe is both stranger and more familiar than we might expect. Stranger because the underlying laws permit behaviors we don't observe in daily life. Familiar because those strange behaviors average out or become negligible under typical conditions, leaving us with the predictable, comprehensible world we inhabit. As we come toward the end of this gentle journey through cosmic facts, let's reflect on what we've learned. We've explored how light travels through space, carrying information across vast distances and times. We've examined how planets form through patient accumulation of matter over millions of years. We've discovered how time itself flows differently depending on gravity and motion, flexible and relative rather than absolute. All of these facts share common themes. The universe operates according to natural law. These laws are comprehensible, even when they describe strange or counterintuitive phenomena. The timescales involved are vast, far exceeding human lifetimes or civilizations, yet the processes unfold patiently, reliably, predictably. Nothing we've discussed requires urgency. Light travels at a constant speed, never rushing, never slowing. Planets form over millions of years, accumulating mass gradually. Time passes at varying rates throughout the universe, but always smoothly, continuously, without sudden jumps or reversals. The universe is patient. It has been unfolding for 13.8 billion years. It will continue for trillions more at minimum. There's no deadline, no finish line, no final goal being pursued. The universe simply exists, evolving according to physical law, creating complexity and structure wherever conditions allow, indifferent to whether anyone observes or appreciates it. You are part of this vast cosmic system, made of atoms forged in stars, living on a planet formed from stellar debris, existing in a universe that has been evolving for billions of years and will continue for billions more. Your moment of existence is brief in cosmic terms, but it's real and meaningful in human terms. The universe doesn't need you to exist. It would continue just fine without conscious observers. But you exist nonetheless, able to observe, to understand, to appreciate the beauty and structure of the cosmos. That's a profound gift, temporary but real, allowing you to participate, however briefly, in the universe's self-awareness. As you rest, as you drift towards sleep, you can hold these thoughts gently in mind. The universe is vast but comprehensible, ancient but still evolving, indifferent but not hostile, simply existing, simply being, simply following natural law across unimaginable expanses of space and time. Light continues traveling from distant stars. Time continues flowing at its varying rates. The universe continues expanding, evolving, creating new structures while old ones fade. All of this happens whether you're awake or asleep, whether you're thinking about it or not. You can rest in this knowledge. The cosmos doesn't require your attention or understanding to continue. It simply is, vast and beautiful, strange and familiar, ancient and ever-changing, governed by comprehensible laws, unfolding patiently across time. Let these facts comfort you. The universe is not chaotic or arbitrary. It follows rules. It's predictable, it's knowable, and it's far larger and longer-lived than human concerns, offering perspective that can make our immediate worries seem smaller, more manageable, less overwhelming. You exist in a universe of light traveling through darkness, of worlds forming silently from dust, of time flowing differently in different places. You exist for a brief moment in cosmic time, but that moment is yours, real and valid, part of the vast tapestry of existence. Rest now. Let your thoughts slow. Let your breathing deepen. The universe continues around you, steady and reliable, requiring nothing from you, offering everything to those who look and listen and understand. The gentle light of distant stars falls on Earth tonight, as it has for billions of years, as it will for billions more. Time flows onward, patient and inexorable, carrying everything forward into an unknowable but predictable future. And the cosmos remains vast and beautiful, ancient and enduring, waiting patiently for those who wish to observe and understand and find peace in its vastness. If you found peace in these cosmic facts, if you've appreciated this gentle journey through the universe's patient unfolding, consider subscribing to this channel. We create these calming explorations of scientific truth regularly, offering you opportunities to learn while you relax, to find comfort in the vastness of space and time, to connect with something larger than yourself. The universe has been revealing its secrets for centuries to those patient enough to observe and thoughtful enough to understand. Each discovery brings new perspective, new appreciation for the cosmos we inhabit. By subscribing, you join a community of people who find beauty and peace in scientific knowledge, who appreciate the calming nature of cosmic truth. These facts we've explored together, they're not just abstract knowledge. They're reality. They're the actual universe you exist in. Light really does travel at constant speed across vast distances. Planets really do form through gentle accumulation over millions of years. Time really does flow at different rates throughout space. Understanding these truths connects you to reality in a profound way. It removes the mystery and fear that can come from ignorance and replaces it with comprehension and appreciation. The universe becomes less alien, less threatening, more comprehensible, more beautiful. And perhaps most importantly, it offers perspective. Your problems, your worries, your daily concerns, they're real and valid on human scales, but they're tiny in cosmic terms. Brief moments in the vast unfolding of time, occurring on a small planet orbiting an ordinary star in an ordinary galaxy among hundreds of billions. This perspective doesn't invalidate your concerns. It simply provides context. It reminds you that you're part of something much larger, something ancient and enduring, something that will continue long after your immediate worries have resolved themselves one way or another. So rest now, knowing you're part of this vast cosmic system. You're made of stardust, literally composed of atoms created in stellar furnaces billions of years ago. You exist in a universe governed by comprehensible natural law, vast beyond imagination, yet knowable through patient observation and thought. The stars will continue shining. Light will continue traveling. Time will continue flowing. The universe will continue expanding and evolving. And through it all, the same laws that have governed everything for 13.8 billion years will continue operating, reliable and predictable, creating the stable cosmic environment in which existence is possible. Sleep well, cosmic traveler. You've journeyed far tonight, across billions of light years and billions of years of time. You've learned about the universe's patient processes, its vast scales, its comprehensible laws. And now you can rest, part of this vast cosmos, connected to everything through the simple fact of existence. Temporary but real, brief but meaningful, part of the eternal dance of matter and energy and time that is our universe. Good night. The stars are shining. The universe continues. And you're part of it all.